designer to whatever it is they want to do. But we're going to add this border control agent who's going to check every access that comes across the border to make sure that it's a safe access. So the way this works is, like before, we have a virtual address. We look in the TLB. If that misses, we'll go to the IOMMU, translate it to our green address P. But at this point, the IOMMU is also going to say, hey, border control agent, here, this P, that's a valid address for you to access. And the border control agent is going to remember that, and we can return P back. And now subsequent accesses to P will come across, and the border control agent can check and say, hey, that's okay. We'll allow this access to go to memory, and you're good to go. Okay, if we have a corrupted address Q that comes down to the border control agent, he's going to check and say, hey, wait a minute, you don't have access, you're off to Gitmo or something. So that's the basic idea. So what does border control have to do? Well, I'm not going to spend time talking about the details of the implementation, but it's really simple. Okay, there's one instance of this simple controller. There is, for each accelerator, there's a protection table that stores 2 bits of state per page, obvious state bits here. It's directly indexed by the physical page number, and it takes a tiny amount of memory because it's 2 bits per 4K page. And then the border control agent itself has a cache to cache those permissions, and a single cache entry can hold a whole lot of stuff because it's 2 bits per page. Okay, so if you come back to this comparison again, border controls allows TLBs and caches. It allows them to be customized however the designer wants to customize them, and it's completely safe. Okay, so in summary, for border control, we can block those bad accesses, reads or writes, 2 bits per 4K page, so teeny amount of space overhead. We do have to check them, so we have to access the border control cache. That border control cache could miss, and so there will be some overhead on cache misses. For some simulation data, which I won't even explain what it comes from, the overheads are quite low. Okay, I'd be happy to talk to you more about the implementation and stuff offline. Okay, so that's border control. So that's dealing with writes to bad addresses, reads and writes to addresses that you weren't supposed to have access to. The second thing that we focused on was crossing guard. And really the second part comes out of the question of, well, border control sounds great, but what happens if your accelerator doesn't issue a well-formed request or provides an ill-formed response to a basic coherence request, okay? And so that's really what crossing guard is trying to deal with. And this appeared in ASPLOS in China last spring. Okay, so the threat model here, so this threat model here is what we dealt with in border control. Stray reads can violate confidentiality. Stray writes can violate integrity. And the key thing with incorrect coherence activity is it can violate availability. Okay, so you can cause deadlocks, you can cause denial of service. Okay, so the goals for crossing guard are to allow accelerators to have customized caches, so you can have a high bandwidth cache for a GPU or whatever. We want to have a simple standardized coherence interface for accelerator designers. There are lots of accelerators out there. Do we really want them to have to do a complex coherence protocol, and in fact do one for every host target that they want to work with? Okay, we'd like to make that easier. And then, of course, we want to provide safety for the host system. No unexpected messages, no deadlocks, no denial of service. Okay, so I've talked a little bit already about why we want to customize caches. Let me just say a little bit more. CPU caches have to work with all workloads, so one size kind of has to fit all. Accelerators is a whole different ballgame, right? If you have a streaming accelerator, well, you might want to have a really fancy streaming prefetcher and maybe not such a big cache. For GPUs, well, you need multiple banks. You might want to relax the coherence between the GPU cores, which is what they do. Okay, yesterday we saw a talk about for graph analytics, you might want a bunch of programmable prefetchers, right? There's lots of reasons why you might want to customize the cache for an accelerator. Well, why do we want simple interfaces? Well, coherence is hard, okay? There are a bunch of different systems out there. Each one is different. They have different constraints, And it's a lot of work to make it, to design your accelerator to work with each of those. There's already an industrial effort called C6 to try to make it easier for people to design accelerators. So this is evident, we see this as evidence as people care about this problem. Okay, this is a real problem that needs to be solved. Okay, the other reasons are, well, host protocols are generally proprietary. And there's this whole issue of, well, if I want to do, get access to Intel's Massive protocol, can I? Right? That's difficult and perhaps expensive. It's also the case that they're really complex. So let's give an example of why they're complex. I know, some of you I know this, some of you have probably never seen this. So this is a little piece of a coherence protocol. If you ever look at a textbook of a coherence protocol, you might see something like this, or a state diagram version of this, where you've got 5 stable states. Those are the letters on the far left column. And then across the top are various events or messages that can occur. So an instruction fetch, a load, a store, an invalidate, some other message types, right? And you always look at this, you say, oh, coherence protocols, they're not so bad, right? And the problem with that is that this is only the stable states. Once you add all the transient states and all the other corner case events that occur, you get what we usually refer to as the big scary table. Okay, and so there's lots of work done on trying to verify these things. Dan Soren is very much at the lead of that, and this stuff is hard. Okay, so we would like to make it simple. So why ask accelerator designers to say, go do this, do it for ARM, do it for Intel, do it for AMD, and so on, right? We don't want them to have to do that. Okay, what about safety? Well, I'm not going to dive into too much the details here, but basically that table is basically codifying a set of actions that the cache controller is supposed to take in response to various messages. Okay, so for example, and this example shows that the accelerator cache in red over there on the left has the block with address A cached in state I, which means invalid. That means it doesn't have a valid copy. It's not a real copy. So if another cache, say cache 2, makes a request for that block, it really shouldn't do anything, right? But what if it does? What if it says, due to this bug, it says, hey, I've got a copy, here's an ACK, right? What's going to happen to the system? Well, I'm not entirely sure because it depends on the protocol, right? But I can guarantee you it probably won't be good, okay? And so that's the kind of thing that we want to stop. Or if it's supposed to respond and it doesn't, well, that's, you can end up with a deadlock that way. So there's lots of nasty cases that can occur, and we'd like to prevent those from happening. Okay, so that's the goal of Crossing Guard. How does it do that? Well, again, like border control, we're going to implement a small amount of hardware in the trusted host to ensure that whatever it does do, whatever the accelerator does do, it's going to be safe. Okay, so we're going to implement a simple standard interface. It's got to be complex enough to allow for hierarchical protocols with various optimizations. It's got to work with a range of protocols. It's got to maintain safety for the host. And of course, it's also got to be compatible with border control protections and enforce those as well. Okay, the key idea here is we're going to move the protocol complexity into the Crossing Guard hardware so that only that hardware has to deal with all that complex, that big scary table. It's going to be implemented once per host system. It's going to be designed by the host expert team. So you're not going to say, oh, this accelerator team is going to do this. No, these are the guys that implemented the coherence protocol for Intel or AMD or whoever. Okay, so we talked about 3 goals that we wanted to meet. So the first goal was we wanted customizable caches, and we have demonstrated, I'm not going to give you all the details here, but we've demonstrated that you can both support private per core L1s per accelerator. So this is showing 3 accelerators each with an L1 cache and a Crossing Guard agent for each one, which is going to ensure that each one is going to talk correctly to the host directory and L2 cache along with and so coexisting with the CPU. Or we can also do a much more complex 2-level cache where there are private L1s and a shared L2 for the accelerator. So this kind of matches what most GPUs do today. And again, there's a Crossing Guard agent that's going to ensure that whatever it does when it talks to the green host directory in L2, it's going to do so correctly. Okay? Rather than requiring the accelerator directory, the accelerator implementers to implement the big scary table correctly, they can get by with a much simpler protocol implementation. So this is the the complete protocol table for the single level accelerator cache. So there are five states. One of the B state is the only transient state in the protocol. And if anybody has done protocols, you shall go ooh, because that's unheard of. It's a very, very simple interface.
That's just coherence between the GPU and the CPU, and not between the core and the GPU, right?
This is focusing only at the interface between the accelerator, whatever it is, and the rest of the world. We can come back to that question, but I got to finish my talking very fast. So let's see. So so simple interface. So we also proven or demonstrated that this interface is sufficient to handle multiple different host protocols. We have implementations that work with an AMD HAMR-like exclusive MOSI protocol and a MESI inclusive protocol. So they're quite different protocol implementations. And shown that the host and accelerator protocols choices can be made independently. And then for safety, we've shown that crossing guard is sufficient to guarantee that accelerator requests must be correct, because we're checking them, and we're checking them against the stable state and the transient state, the stable states and transient states of each block. And responses are also checked against the stable and transient states. And also there's a temporal responsiveness that's necessary. So if you're supposed to respond, you got to do so in a reasonable amount of time, or we're going to take notice. Okay. And then also enforce the border control protections. Okay, so just to summarize, Crossing Guard provides a simple standardized interface to ease accelerator development. It guarantees correctness when the accelerator is correct. It provides host safety when the accelerator is incorrect. And I didn't show you any of the data, but we show that there's very low performance overhead. So just to summarize my talk, I think we all know that accelerators raise new security concerns and questions. And what we've shown is that we can design secure interfaces to prevent bad memory accesses, to prevent coherence bugs, to ease accelerator development, and do all of this at low overhead so somebody might actually want to use them. Okay, so I'm happy to take some questions, but I'll leave you with the list of papers which sort of describe crossing guard, border control, and then also a third paper which kind of talks about this threat model and taxonomy for third-party accelerators. So if there are any questions?
Thank you very much. Thank you very much. We have definitely time for a couple of questions. So how is it? It is on. Okay. So are there any questions? Yes. Okay. I see something there.
Thank you. Okay. Quick question, long answer maybe. Matt Evans from ARM. Hello. How are you going to get these technologies into C6? This looks useful.
I think the way we get these technologies into C6 is to keep giving talks like this with people that might be on the C6 team, and yeah, I mean that's I think the right answer, because it's I mean what we've done is not going to go directly into C6, right? But it could, and if there's anybody on the C6 team, I'd be happy to chat afterwards. So okay, we're good, we're there. So.
Hey. Hi, quick question. You said you verified everything is correct. Could you clarify what you are using, like formal methods and stuff like this?
No, we have not done a formal verification. I would say we have demonstrated that it could, that is likely to work. It'd be the more correct thing to say. I mean, but from the sense of, I mean, it's really simple hardware, right? I mean, you are checking. I didn't get into the implementation for crossing guard. Let's talk about border control, right? Border control is saying, if the OS has a page table permission saying you can read or write this, then we're going to verify that, with this little lookup, right? So that is, I mean, yes, it needs to be verified. It doesn't really require formal verification to prove that correctness, right? The more difficult verification thing would be in an implementation of crossing guard. Is it a correct implementation of a correct transducer between the interface that we're presenting to the accelerator and the host protocol? That is going to require formal methods. right? We didn't do it because it's not it's not worth it for a research demonstration, but for a commercial product, you absolutely would want to use formal methods to do that. But that's going to depend on the specific, protocol that you're using, and the framework that you already use to verify the underlying protocol, right? So, okay. Did I answer your question sufficiently, or I kind of? Okay. I mean.
Okay, so we don't really have.
Okay.
No, we have time. We have a few seconds.
The overhead in both of them is that we're going to do a lookup where you didn't need to do a lookup before. So it's on the order of a small cache, because these things have actually in crossing guard, in some of the implementations, you're going to have to do lookup anyways. There's other cases where you do some lookups that you didn't need to. So there'll be a little bit of extra latency. Accelerators tend not to be latency sensitive, and most of the successful ones anyways. And so we didn't see that as a big problem. We evaluated it against GPUs, which are not latency sensitive. Okay.
Thank you again. There's a slight change with respect to the printer program. The next talk will be given by Adrian Tang, and it's on the perils of security oblivious energy management mechanisms on ARM SoCs.
Correct. Thank you for the introduction. It's really great to be here. Hello, everyone. I'm Adrian from Columbia University. So this talk today I'm going to give is based on our work that we presented in Usenix Security Conference last month. It is joint work with my two advisors, Sal and Simha. And today we're really excited to talk to you about how we broke energy management, a fundamental component in all the systems that we have today. So this represents a new class of attack surface on systems, and we call this this class of attacks clock screw. Doesn't work.
Oh, this one should be. Yeah. Well, okay, maybe the batteries are.
Yeah, it's fine.
I see a red light, but.
Yeah,
Okay, sorry.
that's okay.
Maybe that one.
No, it's fine, yeah. So today, as we know it, energy management is indispensable. In fact, none of the systems that we have today can exist without energy management. So this is because, as shown by this chart over here, energy density is getting to a totally ridiculous point. So as we try to cram more and more functionality into the chips, we can create hotspots in them, so much so that if we don't manage the energy well, batteries will drain really quickly, and or worse, we may even burn a hole in our chips. So clearly it's very important. Because it is so important, practitioners in the industry and researchers in the academia have gone to great lengths to optimize the way we manage energy consumption. So this is clearly very important. So in summary, we have these mechanisms, energy management, that we cannot live without and found on almost all the systems and is extremely complicated. So this is a perfect storm for security. And yet no studies have actually looked at this. And so in this work, we study the mechanisms and show that these systems can be fragile in terms of security. Our attack idea is this. Through software, we manipulate the energy management parameters to stretch the operational limits of the devices in a way that induces faults in security critical software. So why is this cool? This is because it allows us to sidestep all the requirements of traditional fault attacks, like needing physical proximity, separate equipments, and all the messy business. But more importantly, this opens up a very new attack surface on something very pervasive on the systems. And it also raises the possibility of doing fault attacks remotely. So in a nutshell, what have we achieved in this work? One, we found a new software-based attack vector that exploits the mechanisms that is very pervasive on the systems. And we show that this vector can be used to break the security guarantees of trusted execution environment, which happens to be the building block for many security critical applications like digital rights management and secure boot. We disclose our findings to the vendors, whose chips are going into hundreds of millions of devices out there. When we spoke to them, the vendors accepted our disclosure as highly critical and valid, and also very novel. And they're currently working towards mitigation and fixes. And finally, we hope that security can be duly considered during the future designs of the systems. So for the rest of the talk, we will first do a deep dive into a very widely used energy management technique. We will describe the hardware and software support for that and how it provides the building blocks for the attack. And next, we would outline the challenges that we face and how we overcome them in the attack. And then we describe one of the attacks that we have in the paper, in our Usenix paper. And finally, we conclude with some thoughts and key takeaways. So recall that we want to stretch the energy management parameters beyond the operational limits of the device. So to do that, we exploit the existing software support for a technique called DVFS. It stands for Dynamic Voltage and Frequency Scaling. So first, let's investigate the underlying hardware regulators and that supports DVFS. There are two main factors that affect energy consumption. You have the operating frequency and the voltage. The higher the frequency of the voltage, the more energy consumed. So DVFS saves energy by turning these two knobs based on the runtime computing demands. You can think of it like putting a rubber band over both the knobs and carefully adjusting both at the same time. So of course this sketches DVFS at a very high level, but in practice, how are frequency and voltage actually change on, say, your phone, for example? So this is possible due to a combination of hardware and software support for DVFS. At the hardware level, we have the circuit-level hardware regulators that control frequency and voltage. At the software level, we have the power governors that monitor runtime usage and initiate frequency and voltage changes using the device driver. By studying the source code of the device driver, we know that the software can control the hardware regulators via memory map registers. So this is really interesting because now we know that software can control some physical aspects of the underlying hardware. And so we focus our study on the regulators and their interfaces. For illustration, here we show the schematics of the frequency and voltage regulators. We reverse engineer from the Nexus 6 device. The important point to note here is on this schematics is that these regulators are configurable from software through the memory map registers. Now we know software can control frequency and voltage on the devices. A fair question to ask then is whether any limits are imposed on these configurations. What we have here is a Nexus 6 device advertised to run at 2.7 gigahertz. We measure the vendor recommended frequency and voltage at runtime. So the frequency we have is on the y-axis and the voltage is on the x-axis. After the measurement, we observe several discrete frequency and voltage operating points. So true enough, if you look at the top right-hand corner here, the highest frequency of 2.7 gigahertz is indeed as advertised. Now we would use the software interfaces that we described earlier to control the frequency and the voltage. For every voltage, we push the frequency upwards until we see some kind of instability. So this ranges from apps crashing, the device rebooting, or the device freezing. And we measure the frequency and voltage and plot the points here on the same figure. So here are the operating points based on our manipulation. As we can see from this graph, two things are apparent here. Number one, so there are indeed no safeguard limits in the hardware regulators. And number two, when we reduce the voltage, that also lowers the minimum frequency we need to see some kind of instability. So besides the Nexus 6, we also found similar behavior in other devices. So these are two of the devices that we tested out within our work. So now that we know that we can change the frequency and voltage with no limits at all, the next thing we want to assess is how dangerous this is on commodity devices. As we all know, ARM devices come with trust zone technology to isolate trusted execution environment to protect, say, your cryptographic keys or to enable like secure boot. So does DVFS operate across the security boundaries that are enforced by trust zone? Well, according to ARM, DVFS should not operate across security boundaries, well, in theory. So I'd like to draw your attention to two things. One, the recommendation is very, very recent, dated last year, August. And this is only based on the ARM v8M architecture. I cannot find something similar for the ARM v7 architecture. And according to the recommendation, any control registers that it can influence the clock, which can in turn affect the software running in the trust zone, they should only be accessible from the secure state. But all this is in theory. So what happens in practice? So this is a simplified view of a trust zone-enabled ARM core. Trust zone isolates the trusted code on the left from the trusted code on the right. And in our research, we found that the underlying regulators operate across the security boundaries. Both the trust zone code and the normal untrusted code share the same frequency and voltage regulators. When the untrusted code changes the frequency of the voltage, it affects the execution of the trusted code within trust zone. And now we know that we can affect the execution of the trust zone code from outside trust zone. So in some ways, maybe the vendors made this design decision to reduce the latency of the DVFS changes, because if you were to follow the ARM's recommendation, it means that all the DVFS will have to be done within trust zone. Now here's a quick look at how much latency each context switch from the non-secure world to the trust zone world would take. It actually doesn't seem too bad here. Perhaps as a form of defense, it may be necessary for us to consider to incur this cost to be a little bit more secure on the devices we have today. And now that we have explored the energy management mechanisms and their interfaces, we've uncovered several building blocks to an attack. In the next section, we will describe how we piece things together for an interesting attack. Ultimately, we want to ask, can we attack the trust zone code execution from outside trust zone using purely software-only control of the hardware regulators? The idea is to push the frequency and voltage past the operational limits of the devices to induce timing faults, and ultimately to break the confidentiality and the integrity guarantees of ARM trust zone. Note that we are not looking at availability here because it is trivial to break that over here. So before we talk about injecting faults, I want to give a quick sketch on why faults occur on the systems when you increase, say, your frequency past the recommended limits. Now, if you look at the devices we have today, all the digital circuits are made up of electronic components, and I call them flip-flops here. Think of them as elements that store some kind of state, say 1 or 0. Each flip-flop has like an input and output. Because there are so many flip-flops here, they need to coordinate their operation with a common clock. The flip-flop can only change their state together at each clock pulse. And data needs to flow from one flip-flop to another, and usually there's some kind of intermediate path in between. Say we want to transfer a bit 1 from one end of the flip-flop to the next. It takes time to propagate this data bit. But more importantly, it needs to do it within the consecutive pulses of the clock signal. So there is a hard timing deadline in some sense. And say now we want to transfer the bit 0 to the other end. What happens when we increase the frequency too much? So this means that the clock pulses will come in really more frequently at any given time. Since the flip-flop changes its states only at the pulses, this also means that the data may have less time to propagate. And as a result, while the output is supposed to be 0, it remains as the old value 1. So at a high level, if you think about it, this fault actually results and exhibits itself as a bit flip from 0 to 1. For example, in practice, during our memory transfer operations in our experiments, we see faults like the following. Now that we understand how faults are actually occur by manipulating frequency, let's talk about some of the challenges that we face to exploit this. To pull this off, it's very, very challenging to do it entirely from software. These are some of the challenges that we have to overcome. We will outline some of these challenges, and we briefly sketch how we address them. So for one, overclocking requires being able to set the frequency way past the suggested value, and especially doing it on a device which is, say, 2.7 gigahertz. And we have seen earlier that hardware regulators have no limits at all. So in fact, any operating points above the blue slope here is a possible candidate for attack values. And the next challenge that we have to address is that both the attack code and the victim code executes on the same device. So how do we prevent the attack code from attacking itself, or maybe the other non-victim code here? So we exploit the emerging trend that the energy management mechanisms are getting more fine-grained. In fact, many devices, such as the one that we attack here, have separate frequency regulators for each of the core. So we pin the thread execution of the attack and the victim code to different cores on the actual devices, and this helps to isolate the effects of the fault injection only to the victim thread that we want. And the environment that we're attacking is a very complex, is a complex OS. And to deal with that, we have to carefully design our attack to disable the interrupts during the window of attacks. And coupled with core pinning, this helps us reduce a lot of noise during our actual attack. And for many attack scenarios, we need precise timing as to when to actually deliver the injection of the fault, and for how long. We also need very fine-grained timing resolutions for the attack. For example, to give a sense of the difficulty, in one of the attack scenarios, we need to inject the fault within a very, very small window of about 65,000 clock cycle. And this actually happens within the entire victim thread that takes 1.1 billion clock cycle. So this is the kind of challenge that we have when we want to inject the fault in there. So for the timing resolution, we rely on assembly level no-op loops for high precision timing delays. And to guide the timing of our fault delivery, we rely on cache side channel based profiling techniques. With a general attack architecture here, we proceed to attack the two security guarantees of ARM Trust Zone. We explore two attacks in our work. So in the first attack, we break the confidentiality by inferring the secret AES key that is being stored within Trust Zone. Usually with Trust Zone over there, you shouldn't be able to grab or extract this kind of keys from outside Trust Zone. And in the second attack, we show how Corkscrew can trick Trust Zone into loading a self-signed application. So in the interest of time, we will only describe the first attack. Please refer to our Usenix paper for more details on the second attack. So the threat model is this. We have an AES decryption app that is running within Trust Zone. It uses a secret key that cannot be accessed from the non-secure normal world. Now the attacker wants to extract this secret key out from the Trust Zone. And we assume that the attacker outside Trust Zone can repeatedly invoke the decryption app. And next, we assume that the attacker has software access to the hardware regulators and thus can inject the Corkscrew fault during the decryption operation. And what we want to do in this attack is to induce a fault while the AES decryption is happening or running, executing within Trust Zone. So here we show an expected operation where we get the correct plain text from the decryption. Now we will re-invoke the decryption operation again, but this time we will induce a timing fault at the decryption operation to result in a faulty plain text. Now with this pair of correct and faulty plain text, we can apply the differential fault analysis from the Tansel's work to finally infer the secret key that we want. So to induce a timing fault to within the decryption execution, these are some of the parameters that we use for the attacks. The hardest part to this attack is actually to figure out how to inject a 1-byte fault to the 7th AES round during the actual decryption operation. So luckily, we can profile the execution environment of the Trust Zone code using hardware cycle counters, even when we are outside Trust Zone. This allows us to perform timing profiling of the victim app from outside Trust Zone. So the first question we ask is, how long does the decryption operation actually take? Does it actually vary from run to run? Because if it changes too much, we're going to have a really tough time injecting the fault to where we want. So here we plot a histogram of the execution time of the decryption operation. And we see that more than 80% of the invocations take between 800 to 900,000 cycles. So in terms of execution time, there's not much variability in the thing that we want to try to attack here. And next, on the attacker side of things, recall that we're using the number of no-op loops to time the delivery of the fault. So is this an accurate proxy for controlling the timing of our fault attacks? So here we plot the number of no-op loops we use before the actual fault injection against the execution duration of the attack thread. So we see a clear, predictable linear relationship here. So this parameter that we're using actually offers a very, very good proxy for us to time and the delivery of the fault injection. So our differential fault analysis requires our fault model to achieve two things here. We need to exactly corrupt 1 byte within the 7th AES round, and next we will see how we can actually do that in a couple of slides later. So how likely are we able to inject the fault in exactly 1 AES round? Here we plot a frequency histogram of the number of AES round where the fault actually occurs. And we see that more than 60% of the resulting faults are precise enough to affect exactly one round of the AES. And how likely can we actually corrupt exactly just one byte, the ones that we want? So here we plot the frequency histogram of the number of corrupted bytes when we have one AES round that's being faulted. And here we see that out of the above faults that affect one round, more than half are actually transient enough to corrupt exactly one byte. We will end off with a summary of the results for this attack here. It is evident that controlling the no-op loops before the fault delivery allow us to precisely time the delivery of the fault to the targeted AES round. It takes roughly about 20 attempts to induce a 1 byte fault to the desired AES round that we want, and subsequently 12 minutes to conduct the fault, differential fault analysis to get roughly about 3,000 to 4,000 key hypotheses, and after which we could just brute force for the key that we want. And next, we want to round up the talks with some thoughts on the applicability of this on other platforms and possible defenses. So the industry is definitely trending towards finer grain and increasingly heterogeneous designs. So as a result, we're going to see designs which give software more control over energy management. We probably see this on the 64-bit ARM architecture, the newer Intel processors, and in fact, some of the cloud computing providers are even giving the VM guests more power and more control over the power management mechanisms. For thinking about all these security ramifications of these designs is certainly warranted here. And there are possible defenses, both on the hardware level and the software level, all across the different layers of the software, of the system stack. But one thing is clear when we are thinking about the possible defenses that we want. There is no clear defense that can entirely prevent the corkscrew style attack. So many of the design decisions that contribute to the possibility of this attack are in fact driven by very practical and pragmatic engineering concerns. So likely a full system response is needed for an effective defense. So to round up the talk, I'm going to briefly highlight the key takeaways from this work. We discovered a new class of attack surface, mainly enabled by the software interfaces of the energy management mechanisms. And we show that we can actually use that to attack trusted execution environment on devices, on an actual commodity device. So ultimately, this is not a hardware or software bug. It results from the fundamental design flaw of the energy management mechanisms we have on the systems. Such the future energy management designs should definitely take security into consideration, especially in the context of the use of hardware-enforced isolation. And with that, I'm going to end off at this slide, and I'm happy to take questions. Thank you.
I want to thank you personally, because I've been told many times that modern CPUs with a very high clocks, precise faulting would be difficult.
Right.
And you can do that even on device. So thank you very much. I will take this as an example to many people.
Thank
So
you.
are there any questions? Yes, there.
Hi, I'm Peter Svensson from Ericsson. I was wondering about what is new about this attack mechanism. I mean, attacks using allowing control of shared resources such as precisely clock and voltage across trust domains is a known and exploited attack vector for 10 years, which we have designed around in many trusted systems. So what is the actual new thing in this attack vector?
The fact that we can actually influence trusted execution from outside that using purely software-based interfaces. And more importantly, actually forces the vendors and designers to think a little bit closely about like the energy management mechanisms when they're doing all these things. You can actually open up a whole can of like worms, especially when thinking about this.
I think what is surprising is that this is an attack we have in the industry designed against precisely this attack for 10 years. It is surprising that they are still exposed.
Yeah.
Thank you.
Yep.
Yeah, you have time for one or two more questions, depending. No? No further curiosity? Okay, so let's thank the speaker again.
catch me, babe. I'm falling. Come save me, baby. I'm calling.
I'll try to pronounce it correctly. Shi Huan Yo.
Right.
And we talk about making ARM devices trustworthy. It sounds ominous to us, but I mean, okay. So please go ahead.
Okay, thank you. Good afternoon. My name is Shihwan Yu from Dankook University, South Korea. Before making, today I'll talk about trustworthy ARM computers. Before I talk about trust computing, I'll introduce myself a bit more. I'm very happy to be here because my thesis is about mobile virtualization, running virtual machines over ARM devices. So I spent several years for working with ARM devices and working with virtualization, which is born here. So, and after that, I went to some company and did some research, make some research prototype for commercializing virtualization work. And I joined to university in 2014, and I do some research work on security and power performance scaling of ARM devices. Okay, trust in computers. Today I want to talk about trust in computers. And trust is related with some kind of general belief about working things. And the general beliefs about computers is usually my code and my data is correct and legitimate. And you are thinking about your code will work as intended. And your data are correct. Actually, I bought a house a month ago, and I have a debt in bank for about $100,000. And that has to be correct and accurately calculated. Otherwise, it is very difficult to believe the system. And how can we keep trust is presenting consistency in behavior and data. Presenting the same data, if we don't modify, if it is modified by only authorized person or person, then that could be accepted and committed. And people in computers world, people have concerted an amount of effort and time to setting a concept of trust in computers, and they found that integrity in computer security terms is a core value of making computers trustworthy. To keep consistency in code and data mean checking whether the code and data are original and genuine. And without general belief, more than general belief, we need some verifiable proofs. So Trusted Computing Group, established in 2013, specifications around TPM device has been set out, and Trusted Platform Module has been standardized, and it actually measures the integrity of the computing platform. And for ARM, trustworthy computing for ARM is really important. Because ARM is one of the most popular computing platform in the world. So once it is deployed, then hundreds of thousands of computers have trustworthy properties. And especially when you think about some following cases, it is more evident. Smartphones, tablets, and smart devices are delivered to end users. You are buying your phone, and you need some level of security, and you need to work with trustworthy your mobile phone. And there are some special cases, some extreme cases includes some government officers use smartphones. Soldiers also use smartphones. Those kind of devices require one of the highest level of security. And for IoT devices trustworthy is not so obvious at the first time. But when you think about deploying sensor devices to large-scale sensor field, and if you want to have high precision sensor data, and how would you manage those sensor devices? Once sensor device is compromised and it begins to send wrong information, then your sensor devices, you cannot believe in acquire the sensor data, and it can hog some energy of another near-field sensor devices. So security is one of the important property, and to keep your sensor platform integrity, you need to manage those sensor devices, and you need to sometimes monitor and update those sensor devices with some integrity properties, meaning that your sensor devices are running with original code and data. And ARM is making servers, so servers deals with corporate data. So it is obvious in those cases. So many cases that we need trustworthy ARM computers. And unfortunately, trust computing is actually difficult. Even for human society, trust is very difficult. Honesty, behavioral integrity, those are some words that explains trust. And how we can know if a person is honest or not. Since you are not, normal persons are not mind reader, you cannot know how another person thinks. In computer world, there is no things like computer do not deceive person, but you do not know what's actually happening inside your computer. That's because entire information flows are so complex, so it is almost impossible to keep track of the entire information flows. And more, there are human factors. There are some notion like said as benign computing. When you think of security or secure computing environment, then what actually antivirus software company does is usually restricting the execution of some code and restricting the access to some code or data and limiting accesses without knowing what actually happens to the user. So even in the case, some AV companies sends some private information to their company and breaching security, sending personal information. So in the case, humans do not believe in the AV company or some software. So owner should have proper rights to use his own assets. And limiting rights is not so good answer. And that makes people difficult to use computer, and that leads to people likes to find workaround. So basically, trust computing is difficult, and because ARM has many security use cases, ARM has considered security considerations and ARM has unique security features, trust zone from ARM 11. And ARM's trust zone provides separated execution environment, say secure world that is separated execution environment from the normal world, and you have dual set of CPU registers, dual set of caches, and DRAM peripheral devices are controlled by the separate access control hardware. So basically, it is all about isolation, limits access to secure world from normal. So secure world is said to be intact and trustworthy because it cannot be accessible. And this ARM also has some other kinds of approach, virtualization. It was originally designed for accommodating multiple virtual machines workload, and it can be also used as a means of isolating execution environment with some software layer that is called hypervisor. And today I want to compare this trust zone architecture with some other architecture. And that is Intel. And Intel has trust execution technology, TXT. And TXT has 4 components. It has to support virtualization extension. It has to support tamper-proof integrated measurement device. So it needs some new instruction. Say, get sec senter is a specific instruction that prepares clean execution environment. And fourthly, it needs some firmware called authenticated code module. So those 4 key components are essential hardware requirements for implementing Intel TXT. And there are some more software stacks that is specified, standardized in TCG stack. And they are actually originally designed for costly servers. So my question was like, do we need all these hardware elements needed for ARM platforms? And if they are missing, then what is the reason? And why is trust zone enough to make platform trustworthy? So a comparison between Intel TXT and ARM. Intel TXT it begins with the isolated virtual machine environment and starts from the signed firmware. And then it checks all the hardware configurations. And then it measures all the integrity values, making hashes of execution binary and data as a part of tamper-proof measurement in a separate device. And then it boots up operating system and runs with the device driver of inside Linux and operates with the remote side server. While ARM trust zone with the secure world, it is just isolated execution environment. Trust zone API exists for interface between 2 world inter-world communication, and it supports operating system and it supports trusted application. So it is a full stack, separated full stack. And trusted ARM has opened an open software version, trusted firmware, as a part of secure world software. So the implication is simplicity versus flexibility. ARM's trust zone is all about isolated execution environment. So it simply isolates the execution environment and throws all the secure things into this trust zone. While TXT is for measure and validate. It much focuses on measurement and validate. Measurement device, so it needs measurement device, and we need validation software. To run validation software, we need a clean execution environment. So ARM trust zone, I'm not claiming that a trust zone is wrong or bad thing, but it is part of requirements, but it doesn't include measurement device or validation software. So good thing for trust zone, simple model, independent software stack, so all the software can be thrown to the trust zone. But normal world is not trusted, no proofs for secure world, no changes, updates are permitted. On the other side, Intel TXT, step-by-step validation. So we can check if there is a problem, then we can check and we can audit. So we can make execution hash and leaving it as a proof. So we can check which is the problem, which is the root cause of the problem, and we can accommodate changes in trusted software because it is based on the measurement. So when you update your software, then measurement will be changed, and you should have reference value that matches to your different changed hash value. So it is more flexible to accommodate changes. However, it is much complex than trust zone, and it is expensive because you need more hardware. So missing parts of ARM TEE establishment. Establishing TEE in ARM, my first claim is measurement and verification has to be separated. TXT defines TPM as an essential requirement, hardware requirements. And ARM TEE actually has some separated execution environment, but measurement can be performed inside trust zone. And you should verify the measurement also in the trust zone. In the case, how can you believe in the measurement is verified correctly? So to clearly distinguish verification software from the measurement, so we need two separate clean execution environment. But current ARM has only a single one. So the first claim is the measurement and verification has to be separated in separate execution environment. And those are the things, the right-hand side, SINIT AC module, right-hand side, lower, it shows some software code that is distributed by the Intel, which is the validating software. Second claim is ARM trust zone has no admission control at starting the bootloader. Actually, you may think about some secure boot, something like it. And except I will talk about that in separate slide. Without that, actually there is no admission control at starting the bootloader and operating system. Meaning your bootloader has to be clearly verified before it is loaded. And operating system also has to be verified before it is loaded. And so this right-hand side, this is the diagram from Intel TXT. Their yellow rectangle, yellow diamond shows there are three distinct admission control at the booting paces. SINIT policy, pconf policy, MLE policy. Those are checked, meaning SINIT policy checks the version of firmware, BIOS firmware. pconf policy checks the hardware configurations. MLE policy measures bootloader and operating systems. So they are separately checked in the Intel TXT, and ARM have some vague distinction. And even more, there is no security control policies. In Intel TXT, they defined LCP, launch control policy. So only the execution is allowed by these launch control policies. These policies, we can flexibly define those policies and store it to TPM MVLAM. And it is loaded when you boot. But there is no kind of security control policy.
meaning that it is somewhat rigid. When you modify your code or when you update your trust execution software, trust software, then you should be able to give some flexible security controlling policies. So those are the missing parts of ARM Trust Zone. So those some security sensitive devices, we are missing something, and Trust Zone is also necessary, but is a simple solution. So it can be regarded as a secure plinger. So you can throw any security things into secure world, but we need further isolation. And as this is a kind of an example ARM-TE, so I'm here to, this is kind of initiative for making ARM-TE. I'm claiming that we need two separated, isolated execution environment, one for measurement, another for validation. So there is a secure world, trust zone, existing trust zone, and we can take advantage of hypervisor software. So hypervisor software and trust zone, two isolated execution environments. And tamper-proof measurement can be conducted inside trust zone as it is. And you can load security policies within the safe virtual machine, secure virtual machine, and you can validate it inside the virtual machine. You can think of many hypervisor software like Zen or L4 or different kind of library operating system with some lightweight hypervisor. And then we can implement measured launch environment, meaning that you should be able to execute program only after it is verified. And some comments on secure boots. You may know, some of you may have heard about UEFI, Universal Extensible Firmware Interface, secure boot as an optional implementation. And this actually, firmware has public key of operating system and software distributor. Operating system and bootloaders are digitally signed before it is distributed. And when the system boots, firmware checks the integrity using the HMAC mechanism. In this case, you have to think about initial key distribution. Actually, what happened in PC world, Microsoft distributes let all the OEM have their own keys to their firmware. So you can run Windows operating system. However, it doesn't support it by the Linux operating system. So Ubuntu still runs with Microsoft key, and to work around, they use different kind of bootloader instead of GRUB. So in ARM platform, there are several other approaches like using U-boot as a firmware, GRUB as a bootloader. But the distinction between this firmware and software in ARM is very vague. So of course it can be possible, but we have to double check whether it makes sense or not. And this is some things for personal uses computers, personal uses ARM computers. Actually, some antivirus software companies do benign computing, restricting execution and inspecting some programs, innocent programs, making difficult to use computers and snoop your installed program, send it over the internet while you don't know what's happening inside it. And it could be very similarly happen to ARM Trust Zone because Trust Zone is secured and code is not opened. So, and it is in the case, in this direction, ARM could face some security concerns around benign computing. So it is very difficult to earn credit and easy to lose trust. So please keep it open so that others can believe in trust zone technology and code bases. And there are several references around my talk, and so the summary. Trust computing for ARM. To my understanding, trust zone is a simple solution, and that could be improved to making ARM computers trustworthy by separating measurement from validation. To do that, we need to prepare two different isolated execution environments, and we have to mandate integrity measurement before starting operating system at very low level. And we should apply security policies to that. And virtualization is one possible approach to implement another next security execution environment. Thank you.
Thank you very much. We don't have time for questions. We ran a few seconds over. It's no tragic anyway. You can talk to the speaker offline if you have any questions. Okay. So the next speaker is Robert Watson from the University of Cambridge, and he's going to talk, I think it's the ABI of Cherry, and the impact on software stacks. And this continues what we heard yesterday when Simon Moore talked about capability-based systems. So soon this should be connected. Yeah, here it is. So thank you.
Or we should use a microphone here.
We have
Is the microphone working properly? Yes, okay, great. So I'd like to tell you a little bit about our work on Cherry ABI. So this is collective work, a large number of co-authors, especially Simon Moore, who spoke yesterday on the topic of the Cherry architecture, also our collaborators at SRI and the University of Cambridge. What I'd like to do is tell you about Cherry ABI. So we spent the last 7 years developing architectural extensions for security, and this is inevitably a hardware-software project. We have to change the software to use these new features, and so this talk will say a little bit about the process of how we did that and the kind of benefits that we see. So first of all, I will tell you a little bit about the Cherry architecture. I'm going to assume that many of you were at Simon's talk, but I'll refresh you on a couple of bits of it. Talk briefly about our methodology and approach, and then talk about the implications themselves. So what is the impact on software design and security? I was going to mention if you want to learn more about the Cherry architecture, you can go to the website, cherrycpu.org, and also we have our instruction set architecture, which is not just a guide to the architecture itself, but also the design of the architecture and why we went about the way we did it. So maybe we should sort of visit the high-level Cherry software protection goals. So we're interested in protecting C and C++ trusted computing bases, or TCBs. These are the low-level software packages under which managed languages and higher-level applications run, whether it is your operating system kernel, your language runtime for Java or JavaScript, your web browser, and so on. On the whole, in this talk, I'm going to be talking about spatial memory protection and pointer integrity protection. These are going to be the kind of protections that prevent the successful exploit of buffer overflows and control flow exploit techniques and so on in C language stacks. But we do some other things too. We're able to provide foundations for temporal safety, such as reliable and accurate C language garbage collection. We can provide tools in the instruction set that assist in the implementation of higher-level managed languages that do have type safety and memory safety as part of the design. For example, we can provide the safe interaction with native code, such as in JNI, and we can also provide hardware assistance for dynamic checks that are used in higher-level languages, such as bounds checking in Java. We also support scalable in-process compartmentalization. This is the ability to have fine-grained sandboxing inside of processes with substantially better performance properties, actually orders of magnitude better performance properties than current designs. In this talk, I'm going to talk primarily about the first couple of topics. So I will remind you perhaps a little bit about architecture and how attackers see the world. Today's architectures are not designed around a principle I think David Wood mentioned in the first talk, which is the principle of least privilege. Principle of least privilege tells you that you should design software to use and have as little privilege as possible so that when it is inevitably compromised or abused in some form, it limits the damage that can be done. And so when we talk about architectures lacking least privilege, what we mean is that there is an excess of privilege in the representation of the program, and the attacker is able to exploit that excess of privilege. So in a classical buffer overflow attack, which you're probably familiar with, but I'll remind you nonetheless, we allocate some string on the stack. We have a pointer perhaps to the base, and then a length, and software is managing those bounds, managing the indirection implemented through instructions. Our compiler helpfully puts the return address slightly above the buffer. The attacker exploits a bug in the application's handling of the bounds, overwriting the return address. The attacker's value gets propagated into the return address register and then finds itself in the program counter, at which point the attacker now has the ability to control execution of the program. And in the historic version of this attack, we would inject some code into that buffer, and we just run the code that we'd injected. More recently, we have preventions to prevent people from executing data as code, but that's okay. We'll just reuse the code you have in your address space already. We'll borrow bits of your libc or your application itself, and this is well understood technique for sort of return-oriented programming and jump-oriented programming. So we could ask, why is it that these behaviors were things that were permitted at the architectural implementation of the software, given that the C language doesn't really require us to allow the programmer to overwrite target buffers, corrupt and manipulate code pointers, and then to execute data as code, and so on. And the answer is, if we took these privileges away, we would not eliminate the bug would remain, but we would mitigate the vulnerability. We would make it harder for the attacker to use this vulnerability to gain privilege in the system. And the somewhat sad news about the current state of affairs is that memory management units, which are roughly the state of the art in memory protection across the vast majority of systems, aren't really designed to do this. And so Cherry is intended to address this. So if we think for a moment about the behavior of pointers today, pointers are implemented as integer virtual addresses. They're an integer that you load and you manipulate and you index using your load and store instructions. On a good day, they point into a memory allocation or maybe a memory mapping provided by your kernel. And what we like to do with pointers is derive other pointers from them, and we do this through integer arithmetic to move pointers through buffers and around the address space. Once in a while, we will dereference these pointers by jumping to them and fetching instructions or loading and storing data. Today, there is no integrity protection provided for these. They can be injected, they can be corrupted, and so on. They're subject to arithmetic errors. Often these come in the forms of failed bounds checks, but also wraparound and so on, which can be exploited by attackers. And it's quite hard to get these checks right in the C programming language. They're also subject to inappropriate use, which means pointers may be used for things that you don't intend. A pointer into a stack might be used to refer to heap memory, for example. And I guess the point of view from attacker is that code and data pointer manipulation is a great way to exploit systems. You gain a lot of control by manipulating references to code and data. Oftentimes this leads to arbitrary code execution, and that is a very powerful attacker model. There are, of course, other attacker models that have to do with vulnerabilities in application logic, but why would you even go to the trouble to find those if you can simply own the system and run any code you want to? So what we do in Cherry is we try to impose some stronger properties on the implementation of pointers. And you'll have seen this picture in Simon's talk yesterday. If having heard what I told you about pointer derivation and pointer manipulation, you start off with pointers to the address space as a whole, into mappings, and then you subdivide them as you perform memory allocation. Some administrative metadata breaks up and subdivides the total address space, and then we derive pointers and pass them on to the next level of abstraction. So Cherry brings integrity and provenance validity. Integrity means that you can't corrupt the pointer and have it remain valid for dereference. Provenance validity is an inductive property. It says that your pointer has come from someplace via a valid set of transformations. I'll say more about that in a moment. But this prevents attackers from injecting and sometimes from misusing pointers inside the address space. Bounds checking is a familiar technique. Bounds prevents you from using a pointer to one allocation to refer to another. And we actually have quite a strong form of bounds checking. We tie it to a notion of monotonicity. Monotonicity says that once you've narrowed the rights on one of these pointers, you can't then restore them to more broad rights. So this prevents escalating privilege associated with a pointer. And then because pointers don't just refer to data, they also refer to code, we have a permissions mechanism that allows us to constrain what the hardware is willing to use a pointer for. So overall, provenance and monotonicity are going to limit whether or not a pointer can be dereferenced. And if we have that, we have this inductive set of rules that say valid pointers are simply prior valid pointers that have been transformed in a valid way. So the hardware is going to maintain these invariants. You cannot generate a pointer that you can dereference in the hardware unless it's been suitably derived according to the rules. And this is going to let us do things like prevent network data from being interpreted as a pointer. You simply cannot inject a pointer into the system via normal data. We then use bounds and permissions to constrain how the pointers are used, and this is going to be managed by software. The goal is to minimize the permissions and the bounds, because every time you do that, you limit the ability of the attacker to exploit the existing configuration of the system in order to gain privilege. So for example, we can prevent pointers that point to one allocation from being misused to point to any other allocation, even if we're able to manipulate the pointer arithmetic that goes on around that pointer. And once you have this functionality, then you can build higher level software models on top, such as fine-grained memory protection or compartmentalization. So in Cherry, just to remind you, we're going to take our 64-bit virtual address, which is what we think of as the pointer today, and we're going to extend it in various ways to add protection features. And I'm going to describe quite a large object, a 256-bit object, but as Simon mentioned, we have an efficient implementation that allows this to be done in 128 bits. So we will now start adding bits and see what happens. So the first thing we do is we extend the pointer with an in-hardware tag that's going to track the provenance, validity, and integrity. If you want to dereference a pointer, then it has to have the tag present. If the tag isn't present, we're going to throw an exception, so we're not able to dereference it if it's been tampered with. If it's overwritten in memory, let's say the pointer, the tag is going to be automatically and atomically cleared. So if there are race conditions in the updating of pointers or attacks involving buffer overflows and so on, we're able to catch that and prevent dereference. The bounds associated with this pointer are going to give us lower and upper restrictions on the memory that can be accessed. It's not the pointer can't point outside the bounds, you just can't dereference it outside the bounds. We have permissions to limit the operations, as I mentioned. We have some other features. I'm not going to go into detail on those today, but these relate to the implementation of fine-grained compartmentalization. We can have opaque pointers that cannot be dereferenced, whose fields are immutable, and that allows us to refer to other higher-level software objects rather than hardware interpretations of pointers. So we can reuse these protections for software-defined objects. And what I won't do then is tell you about how 128-bit capabilities work or how sealing works. So the Cherry project has been now going on for just under 7 years. We have a portable Cherry protection model. This is abstract. It is architecture independent. We found that it can be mapped into several architectures. This affects how we design software. You know, we program to the protection model, we teach the operating system about it, and so on. And one interesting thing we've learned is that we can really write portable Cherry code that is not specific to the MIPS architecture, which we designed it for originally. Using that model, we then build a specific instruction set architecture. We have a set of extensions to 64-bit MIPS called Cherry MIPS. We have a written specification that you can download. We have formal models that we use to reason about the instruction set architecture. We have a fast instruction set level emulator. We also have an implementation in BlueSpec System Verilog, which is multi-core, relatively simple pipeline processor, enough for us to reason about the impact on pipeline structure, critical paths, and so on. And then we have a large software corpus that we've ported on top of that, and that's primarily what I will talk about for the remainder of this talk. And of course, we perform evaluation to ask questions about protection, to learn about the impact on compatibility and security and so on. And we do that over and over again because it's hardware-software co-design, and the chances of getting it right the first time are pretty low, and we say that from experience. So what are Cherry's implications for software? Well, the first thing is we're providing an architectural memory protection primitive. Primitive doesn't constrain how it is you choose to use it. You just use it in different ways. So as software authors, we can exploit Cherry in different kinds of ways. If we want to take advantage of its provenance validity, we have to know where pointers come from. In particular, we have to ensure that they come from somewhere sensible. If we're going to enforce integrity on pointers, we have to know that transformations of pointers in our software runtime environment don't mess with the integrity. They don't do things that would violate the architectural rules. If we can have bounds and permissions, something needs to originate those bounds and permissions. And if we're going to enforce monotonicity, we want to know that software actually uses pointers in that kind of way. We can also implement software compartmentalization, which uses these same underlying primitives, but as I mentioned, another talk. You'll see in this picture also from Simon, looking at the kind of scope of ways that we can apply Cherry capabilities. We can focus on compatibility without very much protection benefit, or we can slide to the other end of the spectrum. Lots and lots of protection benefit, but maybe reduced binary compatibility or perhaps source code compatibility. So we're able to run unmodified code. We're able to lightly modify code. There are various techniques we can use to make limited use of capabilities. For the purpose of this talk, I'm interested in pure capability code. This is code where we've taken every virtual address, every pointer, and we've replaced it with a capability to see if we can get the software model to work. This will offer us the strongest protection. And we have a Clang and LLV implementation that can target all three of these modes. So if we want to move from this hybrid capability code, which is where we've done much of the research on Cherry over the last few years, then we need a new runtime environment. The hybrid capability code takes advantage of a process on top of Unix, which is basically a MIPS process. Most pointers are integers. So if we want to run capability-aware code everywhere, then the kernel is going to have to understand how to interact with it. The pointers that go in and out of the kernel are going to be capabilities. This is what we've been working on for roughly the last 2 years, looking at high-level software development on Cherry. And the goal here is that every pointer and every virtual address, and by implied virtual address I mean things like return addresses or vtable pointers, everything in the runtime environment is going to be strongly protected. So we want to do this at scale. First, we want to know, can it work at all? But then we have some specific hypotheses. For example, we want to know that all these pointers, implied virtual addresses, either do have valid provenance or that we can ensure they have valid provenance. If they don't, then the program will crash and burn almost immediately. Right. On bounds and permissions, we want to know how small you can make them and still have your software work. The smaller we can make them abstractly, the better the protection properties. Monotonicity seems like a sensible idea. It prevents privilege escalation, but does it interfere with the actual operation of software in practice? And then on performance, can we get sensible performance overheads? We're looking for a couple of percent, maybe in a worst case scenario, sort of 5 or 10%. We're not looking for an 100% overhead. If we want that, we can run existing software bounds checking based techniques. So in terms of methodology, first develop the compiler suite. Okay, we did that. Then develop a set of OS extensions to allow us to run this pure capability code in the first place. That's been a significant focus and is something that's now pretty much come to fruition. We then want to adapt a complete set of applications to run on top of it and exploit the features and look at their interactions. Done that. We then want to measure a whole ton of properties about it. And it turns out that because Cherry exposes more application semantics of the hardware, there are aspects of software behavior that we can study much better on top of Cherry than on top of conventional architectures, which is quite convenient given that we have all these questions. And then we revise all of these aspects as we make improvements. We figure out C compatibility behaviors or OS behaviors, and we do it all over and over again, and we did. So what do we have to do in order to get to a complete Cherry-aware application user space? We need a set of system libraries. We need runtime linkers. We've adapted programs like SSH and OpenSSL, simple programs like BinEcho, and then sort of surprisingly complicated programs like OpenSSL. We've also ported large-scale applications like Postgres, Nginx. We're currently working on WebKit, which requires a slightly more mature C++ environment than we currently support on Cherry. We then want to go around and find all these pointers, and we want to ensure that they have these properties. So we're going to originate all capabilities in a small number of root capabilities provided to user space. User space can't just make these things up. It has to get them from somewhere, and the kernel is where it gets them from. And then we're going to modify our compilers and our allocators and our runtimes to refine the bounds and the permissions wherever possible, because we want to minimize these writes. Sometimes, once in a while, we're going to find there's a trade-off between minimizing privilege or implementing monotonicity and API conformance. So to give you an example, the realloc function, you malloc some memory, you go back some memory with some bounds, and you now want to trade your pointer in for some more memory. And realloc is very clever. It says, oh, actually, if there's enough space off the end of your allocation, I'll just return the same pointer, and you'll know to use it. If I have to go find more space, I'll copy the data and return a new pointer. So that's interesting because realloc is now going to return possibly the same pointer but with more writes associated with it. In Cherry, we associate bounds with pointers, so how do we make that be bigger? Likewise, mmap and mprotect. Mprotect might turn your pointer from being readable and writable to executable. That is a non-monotonic operation, and mprotect does not return a new pointer. So we have to have a pointer perhaps that has more writes, or we have to change the API. So there's a tension between compatibility and privilege minimization. So at a high level, what did we have to do? Well, to get to the point where we could run hybrid code, which is selected capabilities, we made a bunch of changes to operating system kernels. We taught it how to maintain tags in virtual memory. We taught memory allocators to set bounds and so on. From that baseline, we had to do a lot more work. We had to teach the kernel how to have a system call interface, how to deliver signals, the initial process setup. So not only did we have to pass in capabilities, but we had to limit their bounds as much as possible. And sometimes this means changing things around the layout of the process so that you can minimize bounds further. We modified the runtime linker. We had to review and adapt a lot of pieces of software, but I'll show you how much. So the inevitable question when we say things like changing the semantics of C pointers and imposing monotonicity is, oh, I know someone who does some terrible things with pointers. That's obviously not me. So C programmers know that pointers are integers, and they're really quite sure about this, and their software reflects that belief. We know that recent compiler optimizations have been very upset about those conclusions, and one of the interesting things we know is that it's not possible to implement malloc according to the C standard. It's just objects are part of the C standard, so you can't write your memory allocator in it, which is a shame, because that is how we write memory allocators. Also, we now have this other stuff that comes with a pointer. It isn't just an integer virtual address. So we have this out-of-band metadata, the tag. We need to not lose those in places where we would prefer not to, such as in memory copies. And then we have this in-band metadata, which made our pointer annoyingly bigger. but also causes it to be a different width than our virtual address size. What else goes on? Well, we require quite strong alignment of pointers, strong enough that sometimes we find pieces of software that don't like that. For example, hash tables that do not use pointer alignment for pointers. This turns out to be more common than you would like, so I have to change that software. We need memory copies to preserve tags, because people like to copy pointers. They also like to sort pointers, it turns out, so your sort routine had better preserve tags. Slight surprise, it makes perfect sense now. On the whole, pointer arithmetic just works, which is great. And the stupid things people do with the lower bits of pointers also tend to just work. They're just manipulations on the virtual address. That's fine. But casting back and forth with the integers got very exciting. If you, for example, cast one of these wide fat pointers into an integer that definitely doesn't have room for that metadata, we refer to this as a sort of a provenance discarding cast. You've turned it into a virtual address. You're welcome to look at it, but good luck dereferencing it. On the other hand, in our environment, we're allowed to change the size of basic types. It's a new ABI, so we can have an int pointer t that is preserving, and this in general works. And we found that, somewhat to our surprise, because most C programmers don't understand what int pointer t is for, most C programmers use int pointer t correctly. This is shocking. There are some other surprising things about C, or maybe they're not so surprising. There are APIs where people are kind of confused about whether they want a pointer as an argument. So ioctl takes this thing, which is sometimes an integer and sometimes a pointer, but there was no int pointer t in 1974 when the interface was introduced. So we need it to be int pointer t, because we need the kernel to be able to take both there. There are all kinds of cool techniques like nan boxing that allow you to take bits and pointers that happen to align with a not a number bits and floating we generally don't support those very well, but we tell you it's great because you can now tell if something is a pointer because it has a tag. And then we find these interesting things such as monotonicity, changing the semantics of APIs. So you may not think of free as being non-monotonic, but when you free something, you return it to the memory allocator. It has to go find the metadata, and the usual place to store it is just outside the bounds of the memory allocation. So we generally encourage re-derivation of capabilities there. So our JMalloc is slightly tweaked to know how to do that. And then there's some really mind-blowing things. So you get back a pointer from realloc. It has different bounds, but the same virtual address. Is it the same pointer or not? Some discussion is required. And then some surprising and cool but very scary things. If you want garbage collectible C, yes, we can do that as long as you don't allow virtual addresses outside of tagged memories, which changes integer interpretations further. This is the bit where there's probably the most tricky set of trade-offs. We may end up in a place where you pick, do you want garbage collectible C or not? We'll find out. And then some really obscure things. It turns out people like to take functions that accept variable arguments, and then they like to pass them via function pointers that don't have variable arguments and then call them. And if your ABIs differ, bad things happen. So we want to evaluate compatibility. So what did we do? We took the complete FreeBSD operating system. We took all the libraries and the applications. We took major applications like Postgres, and we measured how much work it was to change them. So, and it did require some changes for things like, oh, you're casting things in ways we don't quite like, or you assume things about the alignment of pointers or the integrity of pointers and so on. But relatively few things. So only 34 of the program, 824 programs in FreeBSD actually had to be changed. Although 28 libraries sounds like a lot, you realize a few of those are things like runtime linker-related libraries and memory allocators. So those are inevitably changed, which meant that about 200 out of 20,000 C files and headers had to be changed, which is not so bad. And the good news is that we have quite a few compiler warnings, which will help us identify code that is suspect in our environment. We also want to know that software works when you're done. So we run the BSD test suite and application test suites, such as the Postgres test suite. These generally work out pretty well. There are some areas where we fail. In fact, we found that the MIPS test suite in some places runs slightly better on Cherry ABI. It turns out MIPS is not enormously well tested with the FreeBSD test suite. Right now, we're not running our test suite with dynamic linking, and this explains a number of the failures, but we do run into other problems. We've also found several bugs in the test suite due to buffer overflows and corrupted pointers and so on. Thinking about protection, how do you evaluate protection? Well, you want to do an adversarial analysis. You want to do a historic analysis, look at past vulnerabilities and so on. So the good news is we do eliminate, by definition, a bunch of attack techniques, such as ROP and JOP. If we look back at past buffer overflow-related vulnerabilities, not just memory corruption, but also data leakage like Heartbleed and Cloudbleed, no problem. But also some interesting ones. So stack clash, which was announced a couple of months ago, is one in which your stack pointer is accidentally reused as a pointer into the heap. For us, this is a violation of provenance and an inappropriate use, so we can pick that up without a problem in the Cherry API environment. We can also run test suites, such as the buffer overflow-related test suites, and we find that we perform very well there. So if you compare us to Address Sanitizer, which is a reasonable state-of-the-art of debugging bounds checkers, we come in about the same place. We catch a couple of things that they can't catch. And then I guess a really critical question I won't go into now is, when we look at existing exploit techniques and existing known vulnerabilities, we have to think of it from the perspective of a cherry-aware attacker, right? We have to think about new kinds of exploit techniques, and we're starting to do that now. So I just want to mention a couple of minor things, such as the kinds of ways we can analyze software. So Cherry is quite neat. The hardware is aware of things that are pointers, and it will provide that information to you. We can find pointers in registers and in memory. This is why we can garbage collect. But we can also get extremely detailed execution traces out of the back end of QEMU or an FPGA implementation, which means that we can then analyze all pointer manipulation and use. So for example, we can construct a graph of the provenance of all the pointers and analyze it against the structure for binary and ask, are we getting the right bounds? And we can plot these kinds of things. So here, just briefly mention in this sketch, horizontal axis is the virtual address space. Vertical axis is the passage of time in roughly cycles. And then we can look at where bounds are set. So the horizontal lines are bounds being set during memory allocations or pointers taken to stack variables. And we can visually inspect and understand every one of these behaviors. We can also do some quite interesting things in terms of looking at rights refinement, where data capabilities and code capabilities have leaked to, what capabilities remain on the stack after stack memory has been freed, and we can decide about trade-offs on memory clearing or temporal techniques. A couple of other things we can do. Once we have these traces, we can gather information on the bounds being used. So this is a CDF. So if you look at horizontal axis, this is the size of pointer allocations taking place in memory allocators such as the stack and the heap. The vertical axis is the percentage of capabilities allocated by some particular size. So what we want to do in general is, and these lines are different executions of programs with different bound setting policies, such as does the OpenSSL allocator set bounds. We want to push these lines up into the left-hand corner. We want as many bounds to be as small as possible. And if we're sort of off to the right-hand side, we discover applications are using very loose bounds, and they could perhaps be tightened to reduce the amount of privilege and try to prevent exploit techniques from working. So we can look at this to understand compiler behavior, application runtime behavior, and then we can look at these temporal aspects in terms of data leaks and capability leaks. Just to wrap up, we've spent quite a bit of time learning the hard way about why our software is designed the way it is, because we've been questioning the design choices of all of that software, aspects of runtime linkage and memory allocators, the construction of software at a very low level. In general, when you have these new primitives, it's quite hard to tell what they could be used for, and there are many different usage patterns. So trying to come up with new conventions and decide what they're good for and what the best applications are is quite challenging. It's particularly challenging because once you have these primitives out there and you don't have the opportunity to change them, people will be constrained in what they can do with them based on the design choices you made at the time of creating them, whether it's compatibility behaviors or performance behaviors or the effectiveness for security. And the best way to validate this stuff and refine it is to do the whole stack. What have we done? Well, we created a process environment in which all code makes use of capabilities. This provides us with very strong enforcement of properties that generally come out of the language model, not what we generally compile out of C, but information that is often available in C. It seems to provide pretty good compatibility, strong protection, and although I've not talked about performance, you'll have to take my word for it that it comes with reasonable overheads. And there are some interesting questions that come out of this. I mean, the architecture with Cherry is much more aware of the structure of software because it's enforcing that structure. And we have to ask the question, are there other benefits that could raise? For example, if we expose more information, can we teach pipelines or prefetches or other aspects, cache behaviors, to take advantage of that knowledge to improve performance and not just security? So I will direct you at our website, and thank you for your attention.
Thank you very much. Okay, so I exploit my little privilege of the microphone to ask one question. So how do code and memory usage increase? Have you done some tests?
So we're interested in two kinds of behavioral change. One has to do with the implementation of tags. In general, that is swelling all memory use by 1%, but or slightly less than 1% because it's 1 per 128 bits. But the interesting question is the dynamic cost in terms of DRAM loads and so on. And we are generally finding there, by being suitably clever and yet not assuming that those bits are stored in line with DRAM, that we're looking at, you know, from sort of unmeasurable up to maybe 1 or 2% on pointer-intensive workloads. So it turns out the performance over the head there varies based on how much of the data you're transferring is actually a pointer or isn't a pointer. The second dynamic aspect is on increased pointer size, which certain kinds of applications are very sensitive to, like language runtimes, and then other applications couldn't care less.
So MCF would be worse.
Yeah. So one we're particularly interested in, but we don't have measurements on it, like JavaScript runtimes, where people already use pointer size mitigation techniques. So in the jump from 32-bit to 64-bit, often pointers inside JavaScript runtimes or Java runtimes stayed at 32-bit, even though the rest of the application was 64-bit. So I mean, the good news is those moderations would still work. The bad news is you still wouldn't get the security benefits of using these techniques. So for applications like Postgres, we see really no discernible performance overhead, but they're not very pointer intensive. And then as you kind of push into minimum spanning trees and things, I don't know, 10, 20% performance overhead, because you are doubling the size of every pointer. And if you're really using the things, you should be able to notice. If you can't measure it, then you're not doing it right. But I think we're a bit early to have really conclusive performance measurements there. Also, our pipeline is relatively simple pipeline that is more sensitive to code bloat than to data cache pressure. So we're still optimizing the instruction set, so we can get rid of the ephemeral overheads and get down to the essential overheads.
Okay. Any further questions? Yes. Okay. Faster.
Sima Sethumadhavan, Columbia University. Great talk as always. I was wondering if you could say a few words about the cherry-aware adversary evaluation. If you can.
So this is early thinking. I mean, your attacker has some of the abilities they used to have. They just have a slightly reduced set of abilities. So bounds enforcement, the attacker's not really getting around that. So they have to avoid the use of buffer overflows and so on. They also can't inject pointers, but they can use pointers they already find lying in your address space. So I was mentioning a few times things left on the stack. So we don't provide an explicit, complete architectural solution for temporal vulnerabilities. So if, for example, you have a stack frame that contains a function pointer that is not properly initialized by that stack frame and it dereferences it, then a previous function pointer or return address lying on the stack could be reused at that moment. So it's not that we can't manipulate aspects of the runtime, it's that we're very constrained in doing so. Now, you can't execute arbitrary code, you can only execute the thing that was lying there on the stack at that moment, and yet maybe that gives you more control. Likewise, we might be worried about mem copies that work on larger regions of memory and propagate pointers around, because memcopy is going to preserve pointer semantics, so as an attacker I would want to manipulate that. So right now we are not aware that any of the software we've adapted is in fact vulnerable to these things, but I think if we want to push in that sort of adversarial research direction, that is exactly where I would look. I would look at situations where the attacker either doesn't rely on pointers, so data-centric vulnerabilities in applications, which we don't claim to sort that out, or places where we could manipulate pointers that, for temporal reasons, have been left where they are. And that's why, in particular, we're interested in the temporal analysis in our tracing work to try and characterize, is it worth investing performance overhead in clearing bits of stack, or you could overwrite return addresses as you walk back up the stack. I would have a small overhead, but you could certainly do that. So is that worth it or not? We don't know yet.
So I think the time is actually over. I was hoping for another 4 questions, but well, it was my fault. I had mine as well. So let's thank the speaker and all the speakers of the session. Just a minor reminder, there is a Sun Hilton Hotel key card on the desk in front of the auditorium, and there is a white Samsung phone, and Nida has it.
Come catch me, babe. I'm falling. Come save me, baby. I'm calling. babe. I'm falling. Come save me, baby. I'm calling. Come save me, baby. I'm calling.
welcome to the last session of the day. This is Security 2. I hope you had a really good day so far. Just a very quick announcement is after this whole session, all the dinner drinks will be at the CWB building. That's number 7 on your map. The full name of the building is the Crausaz Wordsworth building. And I'll give you another reminder at the end of the session. So this is a change from the hall balcony. We have a great variety of talks today. I'm sure it's going to cover many of your interests. First of all, I'd like to thank Ross Anderson for coming here today. And he's going to be talking about how security will converge, how security and safety will converge in an IoT world. So, do you want this?
Thanks, Adrian. I have to use a clip-on. Okay, fine. How's that for volume? Is that okay? Good. Okay, so the title of my talk is How Security and Safety Will Converge in the IoT World. A lot of people have started thinking about how you would do standards for security in IoT. And we learned something last year which suggests that standards may come from a different direction entirely. Because the European Union regulates the safety of all sorts of devices. There's over a dozen different verticals with rich, deep regulatory regimes that have evolved over many decades. And last year, the European Union asked 2 colleagues and me, Aaron Leverett and Richard Clayton and me, to do a research project to examine what the Internet of Things would mean for their regulatory infrastructure. Their obvious concern is that once you get software everywhere, safety and security get entangled. So what happens, for example, to the safety of motor cars once every car is basically a mobile phone with an engine and wheels attached? Another interesting aspect when you look at this in a European scale is that safety and security are the same in the languages spoken by most EU citizens. Sicurezza, seguridad, sûreté, Sicherheit, and so on. And so what's going to happen, not just from the point of view of the security world, but from the point of view of safety regulators when people have to cope with this? Now, by way of background, markets do safety in some industries better than others. Planes are safer than medical devices because plane crashes are public and they kill rich white people and they get reported on the front page of the newspaper and they affect company share prices, so people care. People who die from medical accidents tend to be older or poorer or whatever and die unshriven. Cars are one of the examples that we looked at, and cars were absolutely dreadful for the first 70 or 80 years of the motor industry's existence, until a campaigner, Ralph Nader, wrote a book, Unsafe at Any Speed, which so energized the American public that they set up the National Highways Transportation Safety Administration and started setting standards, doing tests and reporting on car safety. In the European Union, we had a different trajectory, but we've got a bunch of general laws such as the Product Liability Directive, which says you can't click away liability for bad things that cause death or injury, and the Framework Directive on Type Approval, which is what regulates the approval of cars for Europe's roads. And there's over 20 European Union agencies, plus some other agencies as well, involved in this. So it is a big, entrenched bureaucratic apparatus. So what does security hold? Well, this is from 2010, from the Car Shark paper at Auckland. Let's see if I can actually cause the video to play. This car is being hacked remotely. So the guy in there, I spoke to him at the conference. He was test driving that car on a disused airfield near Seattle. And the guy with the walkie-talkie was his thesis advisor who had hacked the car and pressed the brake button. And the student said that was the most terrifying thing he'd ever done in his life, much worse than scuba diving and cave diving and stuff like that. But you can imagine how creepy it can be if you're driving along and somebody else can control your brakes. That didn't get much industry attention, but what did was 2 years ago when a couple of guys, Charlie Miller and Chris Valashak, hijacked a Jeep Cherokee by using the OnStar radio system in the car itself. So instead of having to hack into the diagnostic port in the under the car's glove box, all they needed was the car's IP address. And so they managed to take over a Jeep with a volunteer journalist in it and slow it down so that it was driving at 20 miles an hour on the freeway with the big trucks going along honking hard behind it. And eventually they ran it off the road into a ditch. And because this was visual, it got on the front pages of the papers, it got in the news, people suddenly cared. And that cost Chrysler billions because all of a sudden they had to recall over 1 million vehicles for a software fix. So this is moving up the agenda. Here's another example of what happens when cars get hacked. Anybody recognize the guy on the left? This is the former CEO of Volkswagen who put evil software in his company's cars. You can see on the right what happened to his share price when he got caught, and his board of directors gave him the boot. So the attackers are not just outsiders, they can be in the supply chain as well. And in fact, this is an industry with pervasive mistrust. Ford tried to source a series of components for one of its cars with a contractual term that the suppliers would escrow the source code of all the components, and they simply didn't find any takers. So one of the problems with testing cars is that nobody knows all the software that goes in it. Bosch supplies this, Magna supplies this, Volkswagen supplies this, and neither gets to look at each other's source code. Another issue that's coming along is scaling, because although your traditional car makers are moving to autonomy by adding one feature after another, adaptive cruise control, automatic emergency braking, and so on, you've got challengers like Google and Tesla who are moving faster and trying to get to autopilot more or less in one leap. And the software that's underlying this is also interesting because Tesla has already moved to regular software upgrades. When they made autopilot available, for example, that was just a software upgrade for which you paid $5,000. And all of a sudden your car could kind of drive itself on the motorway. Other vendors have said that they will be doing regular over-the-air software updates by about 2 years from now. And because you've got a mutually mistrustful industry with components sourced from companies that basically aren't prepared to share secrets with each other, testing is a real big problem. You can buy test rigs for cars, but they're put together by almost a monopolist company. You'd have to sign an awful lot of NDAs to compete with them, and it is tiresome, it is expensive, and the lab cars, as they're called, tend to be recycled quickly because of cost. Here's another example of the Internet of Things. Could anybody spot the CPU in this picture? This is the intensive therapy unit at the hospital in Swansea. And as you can see, there's lots and lots and lots of CPUs. And as a result, there are lots and lots and lots of accidents. We have a house guest staying at the moment who broke both of his legs in a motorcycle accident 2 years ago, and he almost got killed, not in Swansea, in Southampton, when a nurse was about to give him 150 milligrams of morphine instead of 30. Why? Because of basically because of user interface problems. Here, for example, are all the syringe pumps or infusion pumps that you see in Swansea. As you can see, all the UX is different everywhere. And even where you've got a device which is supposedly the same thing, Bodyguard 545, on this instance, it's a 5 to increase the dose and a 0 to decrease it. And there it's a 2 to increase the dose and a 0 to decrease it. And so twice a year, a new cohort of nurses start in every NHS hospital, and they see half a dozen different types of pump from different vendors, some of which they may have seen before. They don't have to practice individually with each pump, as an airline pilot would with a new plane, and accidents happen. What can you do about that? Well, the medical device directives are now being revised. And this is a big deal because my friend Harold Thimbleby is a professor in Swansea and has looked at this. has gathered evidence to show that in the UK, hospital safety usability failures kill about the same number of people as road traffic accidents. And here the priority is to get regulators to do post-approval studies in adverse event reporting rather than just pre-market approval, which is something you have in common with cars. At present, you do car safety by smashing 200 prototypes against the wall before you start manufacturing the thing, and then you hope it's good for the next 40 years. Similarly with medical devices. As we move to a world of pervasive software which gets updated, you have to start looking at safety throughout the whole life cycle, and you have to start looking at stuff that people didn't look at before, such as the user interface. And security is going to help to drive this, because up until now, if you get killed by a syringe pump, if my mate Marky had been killed a year ago in Southampton, probably nobody would have noticed because he was pretty sick at the time. But if they had done, it would have been the nurse's fault. People seem to be good with that. But attacks are very much harder to ignore. And now that you're seeing attacks on medical devices, we're starting to see serious product recalls. In 2015, a Wi-Fi hack on the Hospira Simbe confusion pump led the FDA to blacklist it and order a recall, despite the fact that there were over 200 devices on the market which were unsafe, which the FDA had refused to recall. But once you start talking about adversarial action, people get creeped out, regulators panic and stuff gets recalled. Just recently, almost 500,000 pacemakers, most of them in the USA, but some here in the UK have been recalled because somebody found a vulnerability. And this causes all sorts of problems, because when you do software upgrades, you break certification, and there are whole stories around that as well. But what this is telling us is that you need a proper safety and security life cycle for medical devices, just like you need it for cars. The third vertical that we looked at was electrotechnical equipment, electricity substations, smart meters, everything in between. And with substations, you tend to have a 40-year life cycle, and the thing is built using protocols, DNP3, that don't support authentication, just like CAN bus in cars. It's very difficult to retrofit anything because of the huge inertia in the industry and the time it takes to do any standards. And the fact that you get an industry that grew up on private networks and suddenly uses IP networks because they're cheaper means that all of a sudden anybody who knows the IP address of a sensor can read it, and anybody who knows the IP address of an actuator can activate it. And the smart operator here was some guys in British Columbia who realized that the only way to do a practical fix in a short period of time was to reperimeterize. And they set up a company, Belden, which does specialized firewalls that understand protocols like DNP3 and which will sit at the boundary of your substation and not let bad things in from the internet. BP alone has over 5,000 of those, and they sold the company and made a lot of money. So that can work in some circumstances, but it can't work with cars, because a modern car might have as many as 10 different RF interfaces, and not all of these are under the control of the OEM, right? So even things like your tire pressure sensors and your mobile phone Bluetooth pairing and so on can be used and have been demonstrated as being capable of being used for attacks. So that's the big challenge. You could establish non-IT industries using a static approach with pre-market testing and standards that take 40 years to change. And once you get malicious adversaries looking at stuff that's online, then bugs can be scaled into attacks and can be scaled up to stuff that you have to worry about, right? If you have got a vulnerability in a car that could allow somebody to cause 1 million cars to crash at once, that is a strategic threat. And then you need a dynamic approach with patching as in IT, and the time constant's typically a month. What our customers in the European Union were worried about is how on earth you make this work within the sprawling bureaucracy of the European Union. What sort of changes are needed? The sort of questions you have to ask: who will investigate incidents and to whom will they be reported? How do you scale all this up? There's 500,000 serious road traffic accidents in Europe every year. You can't bring in a specialist expert witness every time. How do you automate it? What do you do about responsible disclosure? Right, this is a real problem with the car industry, which usually prefers to keep mum and sue people who blab. How do you bring safety engineers and security engineers together? You know, we read different books, we speak different languages, we publish in different venues, although some industry people are starting to work on that. Are all these 20 agencies in Brussels that work on car safety each going to need somebody who's done a PhD with us on their staff? Well, there aren't enough such people around, and industry offers them more money. But what are you going to do about that? How do you prevent abuse of lock-in? So we ended up with a number of policy recommendations requiring vendors to self-certify for the CE mark that they put on products, that the products can be patched if need be. And in fact, it turns out that we've already got international standards for secure development lifecycle. Anybody who certifies an online and programmable product as CE, in other words, complying with all applicable safety standards, if it can't be remotely patched, is making a false statement, and the customs men at Rotterdam should, you know, send those containers back to China. So there are some things you could do with existing rules if they were enforced. We suggested creating a European security engineering agency to support policymakers and extending the product liability directive to services as well. And then you need to do various stuff around the Network and Information Security Directive to ensure that security breaches don't just get reported to GCHQ, but to your car regulator, your medical device regulator, vendors and so on who can actually do something about it. Here's the punchline. We realized this after we had delivered the report, and last December we were sitting thinking about this at a meeting in Dagstuhl, and we said, well, what's the research takeaway from this? We realized this. With phones and laptops, you patch them monthly, but they become obsolete quickly because you know, Android doesn't want to support 100 different models. That's one type of secure object we make, the frequently patched device that's almost a consumable. And the second type of device is cars and medical devices which you test to death before release, and you don't connect them to the internet and you almost never patch them. Right? And what happens when an unstoppable cannonball meets an immovable post? Well, you have to start revising your philosophical assumptions. What's going to happen to support costs now that we're going to start to patch cars? And since I've started talking about this last December, there has been a huge amount of interest from affected industries. I got invited to talk at Bosch's annual engineering conference back in June, for example, and later when I was talking at Weiss in San Diego, the security VP from Qualcomm comes up and he says, yeah, this is exactly the problem we've got to. He said, you know how many versions of our baseband we're having to keep in patch support for various phone companies who buy our chips? He said, 105. So even among apparently consumable, non-durable objects like phones, the fan-out, the number of different versions of the software that you've got is now starting to cause a real headache. You know, once the embedded phones in cars are 20 years old, you know, Qualcomm's going to have a real headache. And the tier ones, people like Bosch and Magna and so on, they're going to have absolutely astronomical costs. I'll skip through this quickly. Here's my Nexus 5X. Bought it last year. Google announced a few weeks ago they're going to stop patch support in September 2018, right? A £700 device, 3-year lifetime. Why? Because Larry and Sergey don't have enough money to support more than 3 or 4 versions of Android, right? When this world hits the world of companies like Volkswagen and Mercedes, there's a problem. Oh, and this is from the work we do at the Cambridge Cybercrime Centre on security of Android, on what happens if the patch cycle isn't managed aggressively enough. And as you can see, most of the time, most of the devices out there are not secure. So what do you do about this? Well, I heard a large luxury car maker's guy saying that ideally they would like to basically scrap cars after 6 years or so. But there's a small problem in that vehicle lifetimes have doubled in the last 40 years, and a typical car, when it's scrapped in the UK, is now almost 15 years old. And the next problem is that if you buy a large luxury German car, the embedded carbon cost is about 30 tons, which is a bit more than its lifetime fuel burn. So if you reduce the lifetime by 2/3, you can do the math with David Mackay's book, and you'll conclude that CO2 emissions from road transport might approximately double. So we can't really see the policymakers buying that one. And then if you've ever been in somewhere like Nairobi, you'll know that all the cars are about 30 years old. And who's going to patch 30-year-old cars? You know, once at age 20, they've retired from service in the UK and been put on a boat to Mombasa. How do you do the long tail if that suddenly starts being a software maintenance problem? Is there any running software out there, except possibly LaTeX, that's still going 40 years after it was first written? How do we do this? Especially if it's heterogeneous stuff with 100 different CPUs from 20 different vendors written in 15 different programming languages with 30 different tool chains. How on earth do you support that? So here's the implications for R&D. If you have to support 20-year patching, which perhaps the EU might eventually mandate, you need a more stable and powerful tool chain. And the world of crypto teaches us how complex this can be with all the timing and other things that come up with TLS every year. Cars teach how do you sustain all the test environments. They can be expensive, they can be diverse. There's also an issue of how you maintain the skilled staff. Go and read the articles on the Mars Voyager program, which has been kept alive by a dozen engineers, most in the 70s and 80s. You know, working as volunteers, living off their pensions because they're the only guys who know that stuff. Can you run a car industry that way? It's not a labor of love, it's a business. How do you do it? Control systems teach, can you put in small tweaks to the architecture, like control points where you can put a firewall, which limit what you have to patch? Well, that would be nice, but how do you go about doing it? How do you incentivize designers and architects of products to go that way? Android teaches, how do you motivate OEMs to patch products they no longer sell? Do you have to use the big stick of legislation? Or can you do something cleverer? Could you appeal to the self-interest of the component vendors who are the main beneficiaries of extended vehicle lifetime? Implications for research and teaching. Well, since this past academic year, I've been teaching safety and security engineering in the same course to first-year undergrads. And when I told the guys at Bosch, they were delighted about this because they've just put their safety and security engineering practices together into one profession within the company. It's an interesting thing to do, but it's non-trivial. How can you go about making the tool chain sustainable? We've been doing various things, for example, on the security front, trying to see to it that people writing crypto code can use annotations to tell the compiler that, yes, I really do want this loop to execute in constant time, so please don't optimize away these funny instructions that you don't quite understand. There's lots of possibilities for doing things like that, but there isn't time here to even start talking about that. But ways for programmers to communicate and document intent might help, and there have been other talks at this conference which have touched on that general theme. So here's the takeaway message. If the durable goods that we're designing today are still working in 2037, then things are going to have to change. Now, computer science is about managing complexity, right? It's about helping people to roll the stone a little bit further up the complexity mountain before you can go no further or fall off. And the history goes through Fortran and COBOL and Pascal and types and objects, and then tools like Git and Jenkins and Coverity and all the rest of it. All of these enable you to manage bigger, more complex projects. And I think that when you sit down and think about what's involved in maintaining security and safety patch support for a motor vehicle for 20 or 30 years, that's an interesting enough use case that it can help us try and work out what else will be needed for sustainable computing once we have software in just about everything. For more, our paper on the standardization and certification of the Internet of Things is the top link on my webpage, and there's also our blog. So that's where I think much of the interesting research may come from in this neck of the woods over the next 10 or 20 years. Thanks.
So I think we have time for a couple of questions. Do we have any takers? Sure.
Sima Sethumadhavan, Columbia University. I was wondering if you had any thoughts on deterring attackers from attacking these systems instead of asking companies to do stuff. I agree companies must do stuff, but ultimately I think bad guys are going to exist. Are there any policies that you could have, or attack thresholds, or like when we should act, how we can deter them?
That would be the subject of a different paper or a different lecture course. Of course, you punish criminals, but that is a separate matter from seeing to it that everyday devices are reasonably hack-proof and reasonably safe and can be maintained as the environment around them evolves.
Do we have any other questions?
Well, in most Western countries, cars has to pass technical checks every year or every 2 years. Is it conceivable at some point to say, well, sorry, this car is not secure anymore, you cannot bring it to the street anymore, which might help the vendors to stop the lifetime of a car after, for instance, 10 years. If they stop giving updates, sorry, the government tells you that you cannot use the car anymore.
I think this is a very real possibility. In Britain, your car has to pass an MOT, a Ministry of Transport examination, every year after it's 3 years old. And I anticipate that within 5 years or so, having your software up to date will be a requirement to pass an MOT. And that means that if, for example, a law is made in Brussels saying that all cars must be patched for 20 years, that means on your car's 21st birthday, you have to put it on a boat to Africa or else put it in the crusher. What that does to veteran car enthusiasts, I simply don't know.
Was there one more question?
So thank you for your talk. I thought it's very interesting. You clearly highlighted all the great challenges that we will encounter. So my question is very simple. Despite all the challenges, are you hopeful that we'll manage?
Well, I don't think that people who do research on security and safety and on tools to manage system complexity are about to be unemployed anytime soon. I think a more realistic outcome, though, is that we will start to see complexity setting bounds of what's feasible as a matter of engineering. It's already been the case that companies like Microsoft and Google have abandoned a number of big projects because they just couldn't cope with the complexity of them. And if you have got hard externally forced bounds on safety and lifetime and so on, then that will exert pressure on markets, and it will basically set bounds on what can be reasonably achieved by engineers in some areas, which in turn will create more and more pressure for research to push those boundaries out.
Let us give a big round of applause for Ross, please.
Come catch me, babe. I'm falling. Come save me, baby. I'm calling.
sorry, folks. I really thought it would be easier if I didn't use my own laptop. So I'm Wim van der Buijden from University of Glasgow, and I'm going to talk about the work that we propose to do to improve hardware security. So I say propose to do because this is a project that was started in end of February. So these are the partners: Glasgow, Heriot-Watt, another Scottish University, and Imperial College London. And we have EDF, ABB, and Xilinx as industrial partners. So I think the previous talk has much more in detail highlighted all the issues that we could have possibly with IoT devices and so on. So I'm not going to dwell on that for very long. Our focus is on systems on chip, and we want to make the design of systems on chip more reliable, let's say. So more, we want to give the designer a much greater control over the verifiability of the functionality through using advanced type systems. And so most of the talk will introduce what that means. So type systems are programming language features that help us to reason about programs, check programs' properties and things like that. And so in this work has the intention is really to use an advanced type system as a kind of contract that describes your design, and then you cannot implement it without you cannot violate the contract while implementing it, or otherwise your implementation cannot happen. That's kind of the idea. So we call the project Border Patrol, and that's a bit whimsical, I suppose, in retrospect, considering how times were nicer when we were designing this proposal. But essentially it means that we patrol the units of modules in a design. That's what it means. So basically, if you have an IP core in a system on chip design, you don't really know what's in the black box. You have an interface specification. If your interface specification is sufficiently formal, then you can actually create a circuit that will control the interaction between the black box and the rest of the system by patrolling the border, meaning checking all the signals that go in and out of this box. And that's kind of the idea. And by using a variety of techniques, we can do things like check the protocols that go over the connections in the chip, and check the value ranges, and even check derivatives and integrals and so on. So that's what we intend to do. So the reason why we want to do this is, well, if you've written any hardware in Verilog or VHDL, then you know that actually it's very hard to make this formal in any way, to verify that the system exactly does what the specification says, because the specification is not very tightly connected with the actual implementation code. And this is exactly what we intend to change. So we want to make the specification such that if you design in-house and your design does not match the specification, it won't synthesize. If you take a third-party specification, a third-party IP core, and it comes with its specification, but actually it's lying about its own specification, you will catch that at runtime. So that's kind of the idea. So we use a variety of type systems, and essentially, I'm not going to explain all the syntax. I'll try to give you an intuition of what all these things do and mean. But we use session types, dependent types, hybrid types. And what all these things are essentially ways of reasoning about the structure of your program instead of reasoning about the actual implementation of, say, functions in your program. So a dependent type is a type where you can reason about values. For instance, a very simple thing is if you have a type that says this is an array of integers, if you can say this is an array of integers of size n, well, then actually this n could be your dependence, because your runtime value has to be the same as that n. So that would be a simple example of a dependent type. In practice, if you use a language like Idris, which we use here, then these dependencies can be a lot more complicated than that. And they allow us to do things like checking against the ranges and checking against derivatives and so And that's the technology we want to use if we want to see whether values that pass over a bus are actually within the ranges that the designers desired them to be. So with this kind of types, you can essentially very much tighten the kind of code that you can write. So it becomes, in a way, much more restrictive because the type signature, which is this line at the bottom here, which in this case says that you have a vector, an array of size m and an array of size n. If you combine them, then the result must be m plus n. Now, that may seem obvious, but in many languages, you could combine them and violate that constraint, and it would still work. Right? So this is the kind of ability that we have. So another type system that we want to use heavily is called session types. And session types, the easiest way to think of them are actually formalizations of protocols. So it's a formal mechanism to express protocols. For instance, TCP. You could write out the whole TCP protocol as a session type description. And when you've done that, you can prove properties, and you can actually, for every participant in the system, validate its side of the conversation, let's say, and make sure it's correct. And again, this can be done either at design time, where you actually want to see whether the code you've written is correct, or you can use the specification at runtime to check whether what's happening is still according to the spec. So if you combine these things, then you get a very powerful mechanism for, let's say, validating that your system on chip design does the right thing. So this is just an example of a TCP IP handshake implemented in Idris. So essentially, let me see. Did I get? Oh, yeah, okay. So this code here is actually the session type that describes the handshake. So this is not the code that executes anything. That's your specification. And then if you actually implement it, then you see that the type description at the top there has network handshake. So it's basically saying this is a network protocol that must obey this handshake type. And then if you write that code that actually does the handshake, which is very similar the way you would write it in any language except for the weird syntax, if it is not exactly following this handshake type, it will simply not work. So that's the idea. And then we want to use something similar, not to do TCP IP handshakes, but to do protocols in systems on chip. But actually, the concept applies. Now you can say, yeah, but if you have your black boxes, right, you don't know anything about them. The nice thing about session types is that actually there is a one-on-one correlation with finite state machines, which means that actually you can synthesize a finite state machine from the session type that you can use to check your protocol at runtime. So if you wrap your black box into a wrapper that has this checking state machine, then whenever this black box tries to do something that doesn't follow your protocol, then you can stop it from doing that. So that's the main mechanism that we intend to use to keep, let's say, untrusted components from doing any harm to the system. So, however, once we are on a roll like this, we can actually do more. So there is another concept called subtyping. And so if you've written any system on chip hardware and you didn't have a very nice IDE to help you, and you have two different standards, then you have to write glue logic to make them work. You have two bus standards, and okay, that's great. Glue logic, you're very careful, you're a good designer, and you manage. But it would be nicer if you didn't have to, right? So if you use the concept of subtyping, then essentially what it means is that you have a way to say that types are similar in a certain way, and if these types represent your protocols because they are dependent session types, then it's possible to actually either prove that they are compatible, or if they are not, you can actually provide a proof to say what should happen that they are compatible, and then you formalize your glue logic. And the difference is, well, it's formal, it's a proof, you can actually prove that it's correct. If you can then synthesize your glue logic from that, then your chances of getting it right are much higher. So that's kind of, in short, all the machinery that we intend to use to make hardware design much more reliable, let's say. So in practice, it means we need to create some kind of language that you can use as a system architect. For instance, if you would be using Xilinx SD-SOC or something, that has a familiar syntax that lets you express your specification, but that actually ends up being compiled into our type descriptions so that we can do all this fancy type checking. Then we can all check all our own cores at design time, and we don't have to generate any actually border patrol modules for them. And all the stuff that we don't trust, we do synthesize extra stuff to runtime check it. And so the interesting thing is actually, once you say that you have a system that can check protocols and can check values, then this actually applies to software as well, because what you can do is you can start checking whether your software is not exceeding the memory ranges that you have allocated for it, so that it's not trying to tamper with somebody else's memory space. Because you put your checking unit on the bus and you check those calls, right? And so if your software pretends or purports to follow some specification, you can see that it does actually follow it or not. So that way we can actually use it with real embedded systems that don't have just hardware but also software, because there are very few systems on chip that do not have a processor these days. So by doing all that, we really hope to increase safety and security of smart devices and help safeguard critical infrastructure. I mean, that's how it all started. That's why EDF is a partner. They were kind of worried about their next generation of nuclear power plants, something like that. And so we hope that this will be of benefit not only to the people that we keep safe, but also to the academic community as giving a new approach for designing systems on chip. And so I think that's actually already the end of my story. So thank you very much.
Do we have questions? Huh? Okay, so I have one. I mean, tool chains for doing this.
Yes.
Can you just describe like some of the challenges there for, you know?
Well, the way we see it, the challenges would actually be mainly in standardization. But in tool chains, well, we have previous work where we did something like this, but not with session types, purely with algebraic data types. And we integrated it in the Xilinx. In those days, it was called the EDK, so that would be SD-SOC nowadays. So by essentially augmenting the XML file descriptions for IP cores. And we would follow a similar approach. So the challenges are mainly in getting adoption, I think, not so much in getting it into a tool chain, but in such a way that people want to use it. And that's also why we think standardization is really important, because if something like this is not a standard, then why would you use it? Just because it's nice, maybe not. So, yeah.
Any other question? Oh.
Well, sort of on the same theme of standardization, if it's going to be standardized, we want to know it definitely works. So kind of how broadly have you been able to try it on different designs, and you know, is there...
Well, we haven't, because our project only started like 4 months ago. So we've been busy hiring our postdocs and stuff like that, and developing the ideas, but we haven't been able to validate this. But you're right, we would have to be able to make a convincing case in order to get something like a standardization body on board. Right? Definitely.
One more question.
So how would you deal with things that are more dynamic, like things that, you know, parts of the SoC that run firmware, and you sort of like with the topic of patching, you patch something and it kind of introduces a new message type or something into a protocol?
Well, if your SoC is implemented as an FPGA, you could then patch your state machines as well. If it's really an ASIC, then that would require a new run, but then it really depends on how much you care about the security or not, I suppose. Yeah. But yes, if you change the functionality in a way that means that it actually changes the specification, then you have to change the checking of the specification as well. That's right, yes.
Let's thank our speaker. Thank you very much.
Sorry, I have one more
Oh,
thing.
excellent.
Thank you. So if you want to learn more about type systems, we start an online course next week on the 18th. It's free, and you can learn Haskell. So, and this kind of systems, type systems that I've described, dependent types, are now also part of Haskell. So just in case you would like that. Thank you.
Thanks.
Come catch me, babe. I'm falling. Come save me, baby. I'm calling. Come save me, baby. I'm calling. Come catch me, babe. I'm falling. Come save me, baby. I'm calling. Save me, baby. I'm calling. Come catch me, baby. I'm falling. Come save me, baby. I'm calling. I'm falling. Come save me, baby. I'm calling.
Excellent. Right, our final speaker for today is David McCann from the University of Bristol, and he's going to show you how to emulate side channels without actually having access to an expensive side channel lab.
Thanks. So I'm David McCann. Today I'm presenting work I did with Carolyn Whitnall and Elizabeth Oswald, but we also did some collaboration with Kirsten Edder's groups. If you were there for that talk this morning, you might hear some kind of overlap, such as power to software developers is a theme of this talk as well. So the title of the talk is ELMO, Evaluating Leakage for the ARM Cortex-M0 Without Access to a Side Channel Lab. And it's going to present a tool called ELMO, which effectively tries to do that. I don't know how aware you all are with side channel analysis attacks. So I'll give a brief background introduction to what they are. So essentially, these kinds of attacks exploit what is theoretically secure cryptography by using physical properties of an implementation of an algorithm on a real-world device. So in the real world, things happen, and those things can be exploited because they give some information about the sensitive data that's being worked upon. So physical properties can include things such as timing, power consumption, the EM field of the device, and also acoustic noise, but really it's any physical property that could tell you something about the data that's being processed on by the device. So I'm going to focus on power analysis attacks in this talk, and so I'll just give a bit more information about what they are. So these kinds of attacks exploit the data-dependent variation in the power consumption. The actual data being processed by the device is linked to the transistor switches, and then the power is linked also to the transistor switches. So if you can measure the power accurately, then that will also tell you something about the data that's being processed on by the device. And if that data is supposed to be secret, such as a cryptographic key, you're going to learn some kind of information about that. So there are a number of different kinds of attacks which exploit this differential power consumption of the device, such as simple power analysis or differential power analysis attacks. So side channel analysis attacks are really a threat where an adversary has actual physical access to the device itself. So things such as smart cards or embedded devices like in the Internet of Things, that's where you would consider the threat of side channel analysis. So at the moment, the current system, if you want to basically test your implementation to see whether or not it can be attacked using side channel analysis, is to employ a third party. So there are a number of evaluation labs who will charge you an awful lot of money to take your device, do their own leakage detection test on there, and then tell you whether or not it leaks, and perhaps provide some sort of side channel analysis countermeasure to stop it from leaking. So a number of drawbacks of this method are it can be really expensive, and also you have to give your design to the evaluator at a certain point, which can also cause complications. So if we just consider two, here's the pointer around here. Here we go. Oh, that was the wrong button. There we are, it's okay. I'll leave the pointer, I think.
This one's the pointer.
Okay, this one. Yeah. So the top button?
Right. No, the other one. Oh, okay.
That's okay, I'll just point to my hand, that's probably easier. So if we just consider two kind of industries, so one is a well-established industry in kind of the side channel analysis world, that's the smart card industry. So it's a mature industry, large established companies, security is already a priority, so they even have their own conference on the threats of side channel analysis, and lots of access to expertise externally and also internally. But then if we think about another industry, such as the IoT, so here this is characterized by rapidly growing small startup companies where security is not really that well incentivized, and there's limited resources for expertise, so they can't really afford to go to one of these evaluation labs and get them to do a nice evaluation for them. So what's really not available are tools that developers can use easily to just run on their code, and which can basically tell them the information that an expensive side channel evaluation would have told them. And that's really what our motivation is in this work. Our motivation is to develop tools to equip software designers to detect and address side channel vulnerabilities during development, to essentially hand over to software developers a bunch of tools which can tell them what an evaluation lab would have told them and save them an awful lot of money. So the work I'm going to present in this talk is really a step in that direction by plugging a really important gap in tools which are able to do this. and that's by being able to simulate real-world accurate power traces for a given device. So at the moment, if you want to actually do a side channel attack or perform some kind of leakage detection test, you would have to hook up your device to an oscilloscope, measure the power consumption whilst it's running your algorithm. It requires a lot of expensive equipment and a lot of expertise. So this work is trying to sort of abstract all that away so you can just simulate power traces on your own computer. So ideally we want to go from just the instruction set there and then to generate power traces for given inputs and then perform some kind of leakage detection test and then for that to tell us which instructions are vulnerable and which aren't. So that's kind of what Elmo does. So for the outline of the rest of this talk, I'm going to look a bit into sort of previous work, so what's already been done in the area of simulating power traces. Then I'm going to look at our unique sort of model building strategy and the way we go about it, and then finally present our tool, which is called Elmo, which is kind of uses the model building strategy to make something useful. So when thinking about previous work, it's helpful to imagine a line. So at one end there's white box, and the other end is black box. So white box, this assumes you have a lot of detailed understanding of the design of your device, so at the transistor level, and if you know the capacitive loads as well, that's really helpful. You can then build nice models which can give you a nice simulation of your dynamic power consumption. Then on the other hand, if you don't know anything about the implementation, even of the algorithms, and not just about the actual design of the hardware, you can go to the black box, which is just requires a general knowledge of the algorithms, so focusing on just security-sensitive values and operations. But then there's also somewhere in the middle, which we could call grey box. So here you know something about the implementation, but you don't know all the design of the transistors and so on. But for instance, such as the instruction level, at the instruction level, you know the instructions that are being run. You don't know exactly what they're doing in the hardware, but you have some idea of what's going on. People who have tried to simulate power traces at this level have generally just assumed what's called a leakage model. So that's that your data is giving away information according to a certain power model, such as the Hamming weight or the Hamming distance, which is great. However, we know in the real world things aren't this idealistic. So, for instance, we know that the instruction before and the instruction after affects the energy consumption. Well, maybe that also affects the actual leakage characteristics of a given instruction as well. So what we try to do is provide appropriately complex models at the instruction level and then build those into a tool. And so we use actual measured power traces rather than just like assuming a leakage model such as Hamming weight and Hamming distance. We actually get the device, measure power traces with the oscilloscope, and then we use some well-established techniques in the side channel literature to go about profiling those instructions. So the techniques we use are based around linear regression, so I'm not going to spend long on the statistics here. But essentially, for each of our explanatory variables, so an explanatory variable there is something which contributes to leakage. So for instance, the Hamming weight of an operand of instruction might contribute to leakage, or an individual bit of that operand will contribute to leakage, and the Hamming distance and so on. So those are the explanatory variables, and we model them in the form given here, where alpha and beta are chosen to minimize the sum of squares of the residuals. But one thing we do is we want to make sure that everything that we include in our model is actually significant, so that we don't have any sort of redundant explanatory variables in it. And we use the F-test to do that. So we test that things actually contribute to leakage. So does the Hamming weight of the second operand of this instruction contribute to the exploitable leakage? And then if it does, we'll include it in our model. But of course, we need a platform to do this all on. In theory, our methodology should extend to all processors, but we chose the ARM Cortex-M family, and in particular the ARM Cortex-M0, though we did do a partial analysis on the M4. And we mainly chose the M0 because it's widely used and it's the most simple of the variants, which seemed like a good place to start. We don't know the exact, I don't know the exact architecture of the ARM Cortex-M0. Maybe some of you do. But we could assume to help us with our modeling strategy to try and make sure we catch kind of the interactions between the operands of the different instructions. We could gain some ideas about what it might be based on what we know about basic architecture of microcontrollers. So we know there's an ALU, for instance. Maybe there's a hardware multiplier. I know some of the Cortex-M processors have a barrel shifter. The two buses for the operands go into the ALU. And then also the bus taking the value back to the register bank, and then also the buses to communicate with memory. So we only chose a subset of the instructions to profile that can be run on the ARM Cortex-M0, so only 21 instructions. So this was just to make things a lot simpler at the beginning, because it's quite a lot of work to actually profile them. And we just chose the ones really which were used typically in symmetric key cryptography, but also which are likely just be used widely generally. So if you're running something, it's likely that one of these instructions will handle your sensitive data at some point. And I'll mention more about the thumb emulator later on, but it's just basically a really simple emulator of the thumb instruction set on which we build Elmo. So as I said, we actually measure power traces of our device. And to do that, we need a side channel measurement setup. So we use an implementation of the ARM Cortex-M0 on the STM32F0 discovery board, which contains a bunch of stuff which is quite useful. But we made some modifications just to get really good power measurements out of it. So we extracted the power pins and then passed as big a resistor as we could over it, so we could get the differential voltage over that, and from that we could work out the power consumption of the device. And we measured this all on a LaCroix oscilloscope with a sampling rate of 500 megasecond samples, and the device was at 8 megahertz. And we did some averaging as well, just to reduce some of the noise levels in our traces. Okay, so first of all, we just wanted to characterize the basic leakage characteristics of the individual instructions. So we just chose this sequence of 3 instructions. So it was just a move, followed by our target instruction, followed by another move instruction, and then all these were processing random data. And then we modeled it according to what's shown here. So this is basically all the operand bits of the 2 operands, and also all of the bit flips, such as the Hamming distance of the 2 operands. So we found that all of these were significant in that, by that I mean they actually contributed to the leakage, so we're included in the model, so that's each bit of the operands for the Hamming weight and the Hamming distance. However, there was some variation in the form of the leakage over different instructions. Before we went on then to look at the effect of the instruction before and instruction after, we looked into making a few simplifications just to try and reduce our problem down, because doing all sequences of 21 instructions becomes quite a lot. And intuitively we were thinking, well, some instructions use similar parts of hardware, so it's likely that their leakage characteristics will be similar. So what we did is we performed a clustering analysis of the coefficients of our linear regression model I talked about previously on all our instructions to see if we could group them together. And so the results are presented there, where if we choose the best silhouette index, that gives us this one here, which groups instructions as ALU, so all the ALU instructions are kind of leaking in a similar way. The shifts are, the stores are, the loads are, and the multipliers. So that's kind of intuitively sort of what you'd expect as well, which is quite nice. So we need to extract one instruction from each of these groups of instructions on which to perform our sequence analysis. So we chose the XOR, logical shift left, store, register, load, and multiply. And so this just shows the characteristics of the coefficients across all of the bits. So you can see there's actually it varies quite a lot over the different bits themselves. So then if we just compare that to the average for the whole group, we can see that our instruction choice actually is quite similar to the average, which means it's quite a nice and representative choice for that group. So then we went on to look at sequences. So we looked at the effect of the instruction before and the instruction after. And for that, we just generated all the possible sequences. So there's only 125. And then we modeled exactly the same as before, so that's all the Hamming weights and Hamming distances. Plus, we also modeled for the previous and the subsequent instructions, so the effect of those on leakage, and also the previous instruction and the subsequent instruction with relation to the Hamming weight and also the Hamming distance. And we found that pretty much all of these had an effect on the leakage as well, so we included those in our final model. So we also then did some tests for higher order effects, so bits affecting other bits, and whether that has any effect on leakage. And our results showed that only the logical shift left and multiply had those higher order effects. So this kind of table just shows a summary of what we found. So for the standard data, all instructions were significant. For the instructions before and after, all instructions were significant. For the instruction before and after and the data as well, then all of those were significant. And for higher order, only logical shift left and multiply were significant. So at the end of this, we've got just a bunch of coefficients basically and models for each of our equations, but we want something useful that can actually then take that and convert that into simulated power traces. So for that, we adapted a very basic emulator, the thumbulator, which then could just take a binary as an input of thumb, and then that implements the model, which I talked about previously, by extracting all the necessary information from the program, such as the Hamming weights and Hamming distances and instruction types, and then it spits out a simulated power trace. And this tool we call Elmo. So now we're in a position to then begin to see what we can do with this tool. So we performed a leakage detection test, which is known as the fixed versus random leakage detection test. So this just takes two sets of traces. The first, a set with a fixed key and a fixed plain text, and the second with a fixed key, but then you randomize the plain text. And by doing a t-test between them, that identifies if there's any power leakage. So this is just an implementation, a few instructions out of the shift rows of a masked implementation of AES. So by mask, that's a side channel analysis countermeasure. So in theory, this shouldn't leak. But if we run this through Elmo, it shows that it does leak because of various interactions between the operands. So this just compares our results using Elmo to real-world power traces for exactly the same implementation. So the red dotted line there, basically if it's above or below that, we would consider it leaky. So you can see that there's actually a pretty good relationship between the Elmo-generated traces and the real-world traces, which is quite reassuring because that shows us that we're capturing the significant leaks. So we've also done a few advances to Elmo recently. So we've actually enabled it to perform automated fixed versus random tests. So now automatically performs this leakage detection test by generating the two sets of traces, and also some facilities to debug with masking, which is a side channel analysis countermeasure. And also because we're basically simulating the power consumption for different inputs, we can also create an estimate of the energy consumption as well from that. So Elmo does that as well. So in the future, what we're going to look at is applying our methodology to different processors, but also automating the application of side channel analysis countermeasures to leaky instructions, because now we can just find leaky instructions. We want to do something about that leakage, and ultimately build Elmo's capabilities into the compiler. And we started working with a compiler company to go about doing that. So the dream eventually would be to compile your implementation, optimize for side channel security, and then for the compiler to sort of do that all for you. So just in summary, we've presented a tool which is able to capture vulnerabilities in arbitrary sequences of code for the ARM Cortex-M0, and it's much more advanced than previous simulators, and it can be used to easily test implementations for side channel analysis vulnerabilities. And our methodology can be used for any processor, any process you want. And so we provided a pretty good step towards giving software developers tools that can provide them with information on the side channel analysis vulnerabilities of their code. So Elmo is available, it's open source, you can get it from here. There's documentation there as well to tell you how to use it. And we've also got a couple of publications which you can go to if you want more information. Thanks.
So we have a few minutes left. Does anybody have questions for Dave? Oh, great.
So you targeted the M0 for this. Was that just because it was an easy target, or do you think this is particularly important for, say, the Internet of Things?
Yeah, that's the other reason. So it's widely used, and it was the simplest of the Cortex M processors. But yeah, that's exactly it. Yeah, it's a very important processor for the IoT in particular. Yeah.
Will you consider application level processors at some point? Or are you just sticking to microcontrollers?
Just microcontrollers for now, but we might branch out.
Yeah, a sort of follow-up question there. I mean, have you looked at architectures where there's actually a cached memory hierarchy?
Yeah, so we've only done it on Elmo to start with. So as I said, like, we chose as the most simple version, but yeah, we will eventually try and look at more complex processors and see if our methodology can be extrapolated to those as well. Yeah, so that's kind of part of the future work of looking at different processors.
Hi, thanks for the talk. But it's not really just looking at other processors as well, right? If you change the board, your results might change as well, right?
Yeah, so I should have said, we did test for manufacturing variances. So we tested over, I think it was 8 of implementations of the processor on the STM boards to check for manufacturing variances. And we found they were very small. But yeah, you're right, maybe with other implementations on different boards, there might be other effects as well, which we would need to test for.
We have time for one more question.
Thanks. Hugo Vincent from ARM Research. We're really interested in helping the community understand side channels on our processes better. What would you like to see from ARM in terms of making your job easier on this sort of a project?
Yeah. Good question. So I suppose one of the difficulties, well, I suppose the methodology in itself is quite neat in that you don't need to know anything about the actual processor implementation. But some more, so there's a lot of trial and error, I would say, to make sure that we found we had the right ordering of the operands, for instance, to make sure that we got the most significant interactions. A question, so if I was able to have asked someone in ARM who knew all this stuff, questions about what I really should be looking for and explaining the problem, that could have been helpful. So maybe some more information there on the actual details of the architecture. Then the other one, I suppose, is just publicity about things like the tools that we're trying to make and what we're trying to do. Yeah.
So I got one more announcement to make before we close the session, which is the pre-drinks, the pre-dinner drinks location has changed and is now in the CWB building, which is number 7 on your map. So number 7. It's also called the Crausaz Wordsworth building. I would like to thank all of the speakers today for such an excellent and diverse set of topics. And I hope you have another great day at ARM Research Summit tomorrow. Thank you all.
Come catch me, babe.